Right, everyone. Welcome to day 3 of the Hypermatrix workshop. I'm very happy to be here with Richard, Libov, and Mano as well here in the room, some people online. So it's been a pleasure to have these 3 days of talks. It's, as I was mentioning to Richard earlier, it's been really exciting to be here in person, to be sort of on location and be discussing these things with a blackboard behind me and everything. So this final day is about hypermatrices proper. So we had a day 1 that was more focused on k-ary algebras. We had a second day that was more focused on hypergraphs and in different ways and rewriting to some extent. And this final day is going to be myself and Josh Grochow, my collaborator, that we're going to present to you some results or some hints at results about some of the products that with hypermatrices. So before that, I'll begin with my talk, introducing some of the basic ideas and what we call hypermatrices and what these objects are for us. And it's going to make a lot of contact with Richard's presentation in particular and Victor's as well. So let me just share my slides. James, if you can confirm that everything is looking good on your end. Let's make it small. All right, excellent. And everyone can see this, right? Okay. So, my question is, what is k-ary associativity? This is the motivating question that I've been thinking about for the last 2 or 3 years. I guess I've been saying 2 or 3 years for a while, so maybe it's a bit longer, but it's essentially that. I haven't had the time until very recently to make proper efforts into it because I was transitioning from a career in differential geometry and theoretical physics. So these topics, although they are closely related, they were not following up any of the previous lines of research. So I stumbled upon this question about, about ternary algebras. So a common friend here, Jose Adolfo Azcárraga, introduced me to my mentor during my undergrad, introduced me to this idea of Lie algebras. So the story is that I was thinking about Lie algebroids, which are a certain kind of generalization of Lie algebras. And so my supervisor at the time pointed me to this paper by Azcárraga, a close friend of mine, but I never knew that he wrote this review in 2010 about k-ary algebras. And there I found that you can generalize Lie algebras also in the number of arguments. So the simplest generalization from a conventional Lie algebra is what we call a 3-Lie algebra, or ternary algebra, sometimes also called a Filipov algebra, that satisfies these properties. So you have a fully antisymmetric bracket. The antisymmetry of the bracket is not so important to me. You might want to think of just 3 Leibniz algebras where you don't assume any antisymmetry of the bracket. But the important one is the Jacobi identity. It's the identity that is written here, which is, it might look messy the first time you glance at it, but it's actually very easy to read. You just need to think about the xy dash operator, which is a linear map, obviously. You just need one argument plugged in the 3rd position. And you can observe that the property is basically that xy bracket has a derivation behavior, right? So when xy acts on ABC, the product ABC, all it does is it hits A first, plus hits B, plus hits C, right? So it's a very simple formula, although it looks messy at first glance. So
a single element is not a derivation, but 2 elements
exactly
define derivation.
Correct. Yeah. That's precisely the.
What about if you interchange y-x?
So in the case of Lie, then you get minus the same element.
Yeah. Here.
And in the case of Leibniz, you get exactly the same behavior, but it's a different map.
Yeah,
because it's for all. Yes. It's the same form. Yes. So actually, in the paper by Azcárraga from 2010, I think it's called a review on Lie algebras or something like that. But you go Azcárraga review Lie algebras, you will find it. There is a detailed account of this particular event. So, in fact, you can find that these derivations form themselves a Lie algebra or a Leibniz algebra and so on. So, the question that really bugged me, so there's a fair amount of literature on these guys. By the way, there's a very simple example of, actually, let me see my own camera, just in case I want to frame myself. Just put a small, well, actually, it's not going to be very useful, so I'll intuitively. I'll just write a small example on the blackboard. So if people are wondering what is a any algebra, maybe you remember from high school that you can define the cross product of two vectors as this kind of determinant formula. So you write x1, x2, 3, y1, y2, y3. Right? And we all know that this is a Lie algebra. This is SO3, right? Just the infinitesimal component of rotation. So symmetrics in three-dimensional Euclidean space. Now, you can see that this formula, the idea of having one line of vectors and the other lines of components of vectors can generalize to any dimension, right? As long as this is a square, you can compute it as a determinant. So what about if we reduce the dimension? Well, if you reduce the dimension, the formula will look like something like this, right? Oh, sorry, it's 2. And then I have only one line to fill, so I'll just write A1 and 2 maybe. And this looks exactly like what you would want to think as a sorry, not this, but when A is a complex number. Right? So this is the complex structure in C, where you see C as basically the two-dimensional vector space, right? So, okay, now what happens when I take it to the fourth dimension, right? So I define a ternary product where I just write the same determinant, and I write E1, E2, E3, E4, basic vectors. And then you have X, Y, Z. These are vectors that you want. We can call them whatever. And then you just use the same. X2, X3, X4, Y1, Y2, Y3, Y4, Z1, Z2, Z3, Z4. So this is just a formula that you compute. And when you multiply everything out, you will find terms that contain some X, some Y, some Z, and some E. Right? So you have just a cubic components on E1, E2, E3, E4. So this thing satisfies exactly that property. If you just compute this long formula, you just check that it satisfies this Jacobi identity. So ternary algebras, and of course you can keep doing this for any dimensions. The higher the dimension, the bigger the determinant you have to write. They all satisfy the corresponding n-1 ary Jacobi formula, which, as you can imagine, is easily extended. You have more arguments. It means that you have to fill all arguments but one, and that argument will behave like a derivation.
So this is Euclidean?
Yes. Yes.
How about in Gaussian space?
So you can actually...
in Gaussian space, you have a natural 4 form, epsilon 0, 1, 2, 3, and you can fit in, but it's more complicated.
You just need to account for minus signs. You just need to account for minus signs.
Yeah. It gives you some properties with light.
Yes.
Light vectors and space vectors.
Yes. Yes. So in fact, in this reference by Azcárraga, you will see the general construction. It constructs it for a general metric, regardless of signature, of any signature. But this construction is very natural. When you think about what this is doing, what this is doing is basically saying, if you give me an n-dimensional metric space, anytime that I define a hyperplane, you will be able to define one orthogonal remaining direction. Yeah. So if you give me enough arguments with an ordering, I have only a unique, well-ordered direction, right? Yeah. And that's the result of the product. So that construction is the canonical example of an n-ary algebra, because in n dimensions you get an n-1 dimensional structure, right? So in dimension 2, we call it a complex structure. In dimension 3, we call it the cross product. In dimension 4, we don't call it anything. And dimension 5, we don't call it anything. But they are these kinds of guys, right? So what piqued my curiosity is that, as I mentioned, for example, the cross product is the infinitesimal component of the group of rotations in 3D, and this is a group. So it's a very well understood algebraic object, right? It has some axioms, and we understand it has a property, and all good. So this is what we call the Lie factor. It has a fancy name, but it's a simple idea that given any Lie algebra, you can find a unique, simply connected Lie group that integrates it, meaning that its infinitesimal component becomes isomorphic to the Lie algebra, right? So given any 2 Lie algebra, so traditional Lie algebra, I can find a group that will integrate it. So in the particular example of the cross product, this process will give you the rotations.
Yeah, you can find only simply connected.
Simply connected, exactly.
The group itself is...
The group is not unique.
Yeah, it's usually...
Other components or other covers. Yes, exactly. So, but the point is that there is such an object that if you define properly, in this case, Lie group, so it's a topological group with the smoothness of the operation, that when you look at the identity infinitesimally, you recover the structure of a Lie algebra.
It's exponential.
Exactly. So you go exponential in this direction, or you go infinitesimal in this direction. So the big question is, if I give you a 3 Lie algebra instead of a 2 Lie algebra, what should I put in here? Right? What is the infinitesimal analog of the exponential of a 3 Lie algebra? So this is an open problem. Nobody knows. It's unknown where you put there. And so I began looking at what I called cubic matrix algebra. So the hypermatrices that we are looking at today, simply to see if I could find some examples of this kind of operations. So I was looking at these products in particular. I'll show you more later. Which I mean, they came from Richard's paper originally, and but also they were sort of naturally defined simply by looking at some combinatorics of indices. So I'm not going to focus too much on that right now. All I wanted to point out is that in this paper from you and from Victor, and Olga and Sitov, there was found that when you scan this product, I think it was in this particular one, I think it was the middle one, if I remember correctly, they were trying to see if for either of these two, there was some axiom, some property that was satisfied. And only this formula was found, and this was mentioned on Monday. This is called a semi-heap, right? And it has this particular property. So what was very interesting is that by looking at the literature, by doing some search myself, some preliminary search, we found out that there was no other known forms of associativity, generalized associativity. Right? Obviously, here the idea is that a group here, which is the exponential of a Lie algebra, has an associative operation. An associative just means that you can group the bracket in whichever way you want. So we were thinking 3 Lie algebras that have this Jacobi identity that look like that might be coming from something that have some kind of ternary associativity, whatever that means in the particular case. And so we looked at the literature, we found that really there wasn't that many options because there was only this. And if you try to make this into a 3 Lie algebra, you can't. It doesn't work in the usual way of building a commutator of one of these. It just doesn't work. So it was very surprising to me that there were no other forms of associativity that were known. So I got curious. And so in order to understand these products, I developed a diagrammatic language just to account for how the indices are being contracted, because I felt like, when looking at these formulas, I was getting a little bit disoriented to see where the indices go. So I just started to draw pictures just to make things a little bit clearer. Yes, and so I actually took inspiration from graph theory, what people do in graph theory, where in graphs you have a adjacency matrix, and this is what we're talking about on Monday, where you have indices, sort of some intermediary index P, and then 2 indices I, J, so you represent the adjacency matrix by this kind of pattern. And the observation here, that what made pictures more interesting than just good guidance, made them mathematically interesting, is that when you study why matrix multiplication is associative, you can directly connect that fact to the fact that there's path transitivity, meaning that if you can connect I to P and P to J, that means that you can connect I to J. Right? So this observation, which is absolutely pedestrian, there's nothing deep about this observation, to me it was really key to try to develop a research program around these products. Okay, so how does this work? It's very elementary, but the basic idea is the following. So if you have a product that looks like the thing at the top, and I'm using some colors just to highlight what indices are being contracted, big disclaimer, the orders of the indices are somehow ambiguous. So you can think that all these are undirected edges or completely symmetric matrices, if you want. We will see that the problem of the order of indices is crucial to get the behavior that you want, but for now, just for the diagrams, just think that they are all fully symmetric, just for the sake of diagram. So I looked at that that definition, and I thought, well, clearly each object ijk has a triangle between three vertices, because that's what I have in the direct generalization that a matrix is a single edge of a graph. So in this sense, a single edge here, a hyperedge, is a hypermatrix. And then all I do is I fill in the colors of the indices that are summed up. Okay, so that has the shape of a fish. That's why we call it the fish. And you heard in Victor's talk that that's how people start to refer to this product now, which is a good thing. This is the other pattern. This was the product in Richard's paper that has this particular contraction pattern. So you see that P with P in the first and second, Q with Q in the first and third, and R in the second and third arguments. So that's the pattern, and we call it 3/4 in case there are any Legend of Zelda fans in the audience. It's just it resembles like that symbol in the video game, so we just call it the 3/4. And then the one that perhaps grants the most attention, at least today in today's session, is the so-called Bhattacharya-Mesner. So Bhattacharya-Mesner wrote a paper in 1990 where they identified a ternary associative scheme, as they called it, which is essentially a ternary relation in a set. And it was defined, or rather, it was, it's not a ternary relation, but it's an operation on ternary relations on a set. And it was defined precisely by this formula. You would have to replace times and sum by and or to get it into a more conventional relation form, but that's essentially it. So this particular pattern is curious because you have a triple index contraction, and you have the standard indices just standing along each other. Okay, so this was the observations that I was doing, and since I joined the Wolfram Institute and I started work there about a year ago, we've been trying to develop a code for this. So can I, it's here. So I'll try to show you that we have implemented Plex diagrams in Mathematica. So you can actually just draw a picture and define a product, which is pretty cool. Actually I need to run. Hopefully this will not explode this time. That's good, because yes, but thanks for the reminder, because I was going to talk over it. But yeah, it's good that I'm just setting the scene. Okay, already. So I'm going to share the screen instead of the window. Give me a second. Where the hell is Zoom? Interesting. Oh, hey, Victor. Didn't see you before. So let me just share this screen, yes. So actually, I don't need this. This should be fine. Okay, so we have coded arrays arrays are the structure that we're looking at. So it's very important that we distinguish. Oh, there's some comments here. So it's very important that we distinguish what is a tensor and what is an array. So an array, for me, is just a list of numbers. There's no structure, no linearity, assume nothing, just numbers in a table. And so the code that we have deals with arrays. It doesn't assume any linear structure, so you can do a lot of things that are not well defined in linear algebra. So they are some kind of artifacts if you have a linear algebraic mindset. But just bear with us because I think there's a lot of interesting algebraic structures there. In this case, for simplicity, we're going to look at just cubic. So square, always what we call regular, right? So regular, it has n by n by n by n. Yes. But of course, many of these need not be regular because if you look at these diagrams, all you require is that the indices that are incident, right? So where each triangle is incident, that dimension is the same. But they can all be different among each other. So you need that the third index and the second index and the first index are the same. Yeah. So for algebraic purposes, we keep things cubic, and not only because of simplicity, but also because otherwise you would not have closed operations. Yeah. Just like in matrices.
Also because here at least you can switch to tensors.
Yes. 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 Exactly. So okay. So. This code just generates so let me, just in case I want to run something live, let me run everything. So this code just generates arrays. So you can see that it's generating, for example, a symbolic 3x3 array. So it's more like a traditional matrix. But we can also generate 2x2x2 arrays over Boolean values, for example, some complex values. You know, we can have this. So I like to show, by the way, I like to call these things the n by n by n arrays. I like to call them cubices, or a cubics, like a matrix, like cubics. And, you know, we have a little funny representation of the thing as a little cube. This can be bigger, of course, can be, you know, higher dimensional, and it's a bit bigger. Or have other representations or whatever. And the point is that these kinds of products, the ones that I just showed, have this kind of shape. They take three cubes and they give you another cube. Just like two matrices multiplied together to give you another matrix. That's just a visual representation of that. So what are those products? So this is what I call contraction operations. And so a contraction operation is a generalization of the dot product or the matrix multiplication product. It's nothing more than that. So you can see here that what I call the operation index contract here basically tells you that you take two indices and then you specify which ones are contracted, and then you specify which ones are kept at the end. So you can see that this in Mathematica language means Hadamard product, basically, so a component-wise product. So index contract, when you don't contract, is just Hadamard product. Index contract, when you do contract, so for example, this is A, B are matrices here, are n by n matrices, 3 by 3, I think. So when you do I, J, J, K, but J is missing from the output, right? Then it means that J has been contracted out. So this equals A dot B, which is Mathematica code for matrix multiplication, right? Okay, so then we define the ternary products. So these are the products. So the Bhattacharya-Mesner is here. You can see that the pattern is IJP, IPK, PJK, which is the same as before. And the output is always, you can see in here, the output is always IJK, 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 IJK. So all these patterns before it, you don't need to get lost in those terms. It's just different combinatorics. And the only constraint is up to orderings, you need to have as many contractions as necessary. So as you were saying on Monday, if you have 9 indices, you'd have to contract somehow 6 of them. But it can be done in many different ways. So, for example, the first one, what it does, it contracts 1 from each input, but 3 times. But the other 2 indices are just not summed over. So you have I and I are repeated in here from the first and second arguments, but they are not summed over. So that is allowed. But for example, in the 3/4, which is the one that Richard used, we have I only in one argument, J only in one argument, and K only in one argument. So these are possibilities. So up to reorderings of these indices, which there can be a few, these are the 5 possible well-defined operations. Okay, so what's interesting about this? Well, there are some properties that they satisfy. So for example, the tree-force, so the identity cubics, let me show you what the identity looks like. So the identity cubics looks exactly as you would imagine. It's what we call an identity array. So the identity array for the 3x3 case is just the identity matrix. The identity cubics will look like this, right? So it will have this form. And so if I take this and I say, I think it's 3D. How do I didn't run this, sorry. So you would see that the analog of this is cubics 3D of this. It looks like that. So it's a cube, and if you look closely, I mean, it's a bit weird, but if you look closely, oh, it's not quite right. Oh no, this is a partial identity. Sorry, this is not the full identity. So this is the identity. Let me just identity array. Okay. So if I change this for identity array, and you just specify that you want it to be Boolean, for example, you want it to be 3 by 3 by 3. So that's the identity array. So you can see that there's all zeros except for 1 in a corner, 1 in the middle, and 1 in another corner, right? So that's what we're calling ID. I don't know if I defined it over here, but that's what we're calling ID. It's here. So if I run this thing, ID is that is the analog, the ternary analog of the identity matrix. So for example, it has some identity-like properties. So if you take it into Richard's product, what I'm calling the tree-force here, it behaves like identity, identity, identity equals identity. Yeah. Just like in matrix multiplication, identity and identity is identity. So it has some similar property. So that's also true with the Bhattacharya-Mesner product, which is this other diagram. But for example, you stop seeing more natural axioms. Like for example, if you do element with identity, you might expect that you get the element back, but that's not the case. At least not for all the possible reorderings. So we have this little code here that checks for all the possible equations that are true with these identities. And so we find some of them. I mean, we find all of them, and some of them, some of the combinations, I mean, are true identities. So in any case, the point here is that arrays have a richer algebra of identities, because it's not only the ternary identity, but also what we call the partial identities, which, as you can imagine, are, if you imagine the identity matrix, you can think of it as being projected in or extended in the vertical direction, in the horizontal direction, or in the lateral direction. And each of them has an identity-like behavior. We call them red, green, and blue because there's 3 of them, and we call them partial identities. So they actually behave in this kind of way. So for example, if I do red, 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 I get red back. But also if I do arbitrary element times green times blue, I get the element back. So there is some subalgebra of those products.
Almost like Rubik's Cube.
Yes, there is some, and that big list over there. That's particularly for the Bhattacharya-Mesner. I could run it for the tree-force as well. So if I do ID search, ID equation search for a tree-force, which is your product, Richard, you see we get some equations. Yeah. We get fewer, but still some equations. And if the equation contains a 5, like these final ones, or even these ones over here, it means that the equation has this. So 1, 2, 3 are red, blue, green, which are these identities. 4 is the ternary identity, which has the diagonal ones, and 5 is a symbolic generic array. So these equations, for example, this one here should be read as red times arbitrary array times cubic identity equals arbitrary array. So it is a identity-like behavior where those two elements are behaving like a neutral element. So for your product, we have all these equations, which is many of them, right? So all these equations are the ternary analog of when you write down matrix times identity equals identity times matrix equals matrix. So those simple two equations become now how many? Whatever, 4 times 10, whatever. It's a long list of identities that we get is the price we pay for being ternary, right? So it becomes much more rich. Okay. So this is about identities. Now, the interesting question that I had in the beginning, what is associativity here? So Richard, this is the code that we wrote to check for computationally check for, so this works for arbitrary products. Any product you want to define, you can put it, and it works for arbitrary expressions. So the way it works is we generate so the arguments look like this. You say find ternary clone equations. You specify the number of products that you want to consider, like the fish or your product or whatever, and you can specify more than one, and they will do all the possible nestings of the products. And then you specify the number of elements that are going to be included. So for example, this first argument here is going to find in the fish product how many equations exist of the form A, B, C equals one of the 3 elements, A, B, C, right? Or equal one of the permutations of the elements. And of course, we all know that the fish doesn't have any symmetries. So the output of that first line is empty.
So I have a question.
Yeah.
But you probably want some very specific equations still, like you don't want to check for any of combinations resulted in anything. You are very specifically probably want to find something very, very interesting, very beautiful. We want to basically brute force with all of them.
I mean, but we don't know what we want to find, so we need to find out anything.
Find it.
Well, you search for everything. You search for everything.
Yeah, but what do you, like, where you can get your intuition what you want to find?
So I was trying to do this by hand and by intuition, and because it was helpless, there's no intuition. You just brute force all possible cases. And if you find some, then you're trying to think, oh, how do I understand this? But first you need to know that some exist, because it's not guaranteed that some are going to exist, right? So
yes.
So
what I was asking was more whether you had also a process of filtering out these things.
No, before we need to know, I mean, I don't know, because before we need to know some, we don't know any.
I understand.
So after you find some, then sure. Once you see some and they look too complex or too simple, then you might want to do something else. But the first step is to know if there are any at all, because we don't know if there are any. Like, that assumes that some exist, and if some exist, then you can do something else. But if the output is the empty set, then there's nothing else to do,
sure.
Right? So anyway, so it's important. I really want to everyone to understand that what this is doing is really checking the clones. I don't know if people are familiar with clones. Clones mean that you basically create all the possible nestings of products. So what this is doing in the first instance is doing fish of ABC, then fish of ACB, then all permutations, and then it computes. So by the way, all the elements are numerical. We generate some small random, sparse random arrays, and then we check all the products numerically. If we get a positive check for an equation of the form fish ABC equals fish ACB, for example. If we get a check, that's numerical, it's just some numbers being checked. Then we write that symbolically, and then we do a symbolic algebraic computer algebra check, right? And so, of course, as you know, Victor here in the Zoom call and Richard know, and many of you, I'm sure, know, the fish doesn't have any symmetries. Therefore,
because it's broken.
Exactly. So, reality check. When we try to find some equations that only involve A, B, and C, we find none. However, when we try to find equations that involve A, B, C, D, E, 5 elements, we should be able to find the axioms that you found in the 2009 paper. And sure enough, we do, right? We find that an expression that looks like this, so fish of fish A, B, C, D, E, is equal, this just not to use equals because that's reserved in Mathematica, but it's equal to fish A, then D and B swapped in here, right? And E. So of course, and then we find all the other equalities, the 6 other equalities. So these 6 equalities are the formula that we had before for semi-heaps. So that's good. So it means that the thing finds what we know exists. So when we run this for example, the Bhattacharya-Mesner product, this takes some time. For this laptop, it takes about a day to run all the possibilities for 5, and it finds nothing. So we know for sure that product has no axioms that only involve 5 elements. Yeah, go on.
No, go on.
Yeah, but could we check maybe next time with Bertrand Leman? No.
Yeah, with the 40
With 40, yeah.
Yes.
So this is
But that would be C3 grade.
yeah. So that will be later because this is primitively the product itself without any. So this is not even considering the vector space structure.
Yeah.
It's only the algebra.
No grading, no.
No, so this is only the pure operation in some sense, because these are sort of pure axioms. Not for example, we're not considering linear combinations.
Yeah.
So in this search, to say that this term equals this term is not equivalent to saying that term minus that term equals 0.
Yeah.
Because in this search, it is really term equalities, right? Exactly, no linear structure, which it's exactly what we want, because the idea was to find the notion of n-ary associativity, not n-ary linearity, which we already understand, right? And so it is very shocking that, at least to me, that when we run, I mean, you can see this is empty. All the other products. I mean, this is again fish table is just another. It's just a fish. So you can see that for all the other products, Bhattacharya-Mesner 3/4, which is the one that you have in your papers, boat, blades, empty. We have no axioms for them. I can tell you that I should have put it here, but I run the same algorithm for 7 elements, where you'd have 3 nested brackets instead of 2, still empty. Nothing comes out. We don't know for 9 because it was too long and we couldn't check.
What do you mean? What do you mean too long? Then it's
Too long that we didn't finish the search.
No, 7 makes sense because it's
For about a week.
3rd iteration.
Yeah, so this is three nested.
From 3 to 5, from 3 to 5 is first iteration,
Yeah,
and from 5 to 7 is second.
iteration. Yes.
But the next iteration,
I had hopes for the 9th iteration, but it's just too long. We didn't finish the search.
okay.
It was just
And it's a
no.
computation. Yeah, I understand.
Yeah.
But computationally, you couldn't parallelize the cluster, whatever it is.
We could. I mean, this is not rocket science. It's just multiplying arrays.
Exactly.
But I mean, we could do it if we really. But this is a. I mean, this is a.
Common sense.
the
Yes.
number of conditions is growing faster than the number of variables.
Yes,
Of course.
it's just because right now the trained models which are really much larger.
Yeah.
Ones.
Yeah. I mean, the point is this is only an experiment. We don't. I mean, because otherwise, I mean, this has no end. Like you don't know when to stop. The fact that there's already this tells you that these algebras have no 5-element term equations. This is already very shocking to me.
Yeah.
I mean, or shocking or mysterious, because it basically tells you that whenever you're doing array algebra, except for the case when you're doing fish, which, by the way, I think I explained on Monday that the reason why, I mean, the way I understand that there is an axiom in here is because you can actually collapse the product into a matrix product. Because you can group indices in a multi-index of 2 and a multi-index of 1, and then you can see the fish product as just A times B transpose times C, right? And because you can do that, and it's associative, and the transpose is strongly compatible with the associative product, then you get an axiom. But in any other situation, which are products that you cannot write as a matrix, as a recombination of matrix multiplication, there seems that nothing happens. It seems that when you ask these products, axiom or what behavior do you have? The answer is nothing. So to me, this was really mysterious. And so this is kind of the punchline of the talk in a sense, that we have the machinery to do these searches and to, if there is anything at all, we will find it. But there might be, as you will see in Josh's talk after me, that there could be an argument for why these products have no term identities whatsoever. This is a proof in progress. So the other thing I wanted to show you is that so it's the Plex diagrams. This is where I left it in my presentation. So so far this is just a matrix algebra in some sense. So interesting. This was it's some error. So Plex diagrams are exactly so this is the mathematical language implementation of the diagrams that I was showing you earlier. So all you have to say is draw a diagram for this number of indices, right? So I have an index 1, I have an index 2, I have an index 3, and then you just group them in terms of the matrices or the hypermatrices that will contain those vertices. So obviously, this diagram represents conventional matrix multiplication, because you say I have a matrix with indices 1 and 2, I have a matrix with indices 2 and 3, and then you specify that you contract index 2. So that's matrix multiplication. So this is the graphic representation of that, which you can see index 1, black, it's a free index, index 3, black, it's a free index, and then anything gray in the middle is going to all collapse and form a single edge at the end. So similar with here, these are two hypermatrices, two ternary hypermatrices, and then you are contracting indices 2 and 3. So the first hypermatrix has 1, 2, 3 indices, the other has 2, 3, 4 indices, and they are contracted at 2 and contracted at 3. So the hypergraph that you draw is precisely this. And this hashtag 1, hashtag 2 is basically represent the order of arguments. So you can, and similarly with Bhattacharya-Mesner, and similarly with blades and so on. So the idea is that there is this function that says Plex to product, which allows you to draw the diagram or specify the indices. And now this is actually something that can operate on elements. So when I write Plex to product of this diagram AB and I compare it to the mathematical code of A.B, it says true. So it means that just by specifying this diagram, I can actually operate on elements. So it's a nice user interface to you can draw whatever product you think is interesting, and then you have something ready to compute on the appropriate size matrices. So here's the few products that I mentioned before. So I have the Bhattacharya-Mesner, I have the blades, which is kind of a Bhattacharya-Mesner-like, because each of these 4 and 5 are contracted like the 4 in Bhattacharya-Mesner, because they are triple contractions.
Here you have to go into 3 dimensions.
Yes, they don't fit in the plane.
Yeah.
And you have the 3/4. This is Richard's product. We have the fish, and we have the boat, which is a kind of an ugly product in some sense, because you have you can contract here, you can contract here. The point is that you have 3 indices left, so it's so. The punchline of all this is that, except for the fish, which we know is a bit special because it can be written as matrix multiplication, for the others that cannot be written as matrix multiplication, we know no term identities whatsoever. And that's the big question. So my approach, I have 2 candidate approaches to deal with this situation. The first one, the first line of attack is to basically naively say, okay, so I'm going to do model theory, basically. I'm going to take the smallest cases of my algebras. I'm going to take 2 by 2 by 2 Boolean hypermatrices, and I'm going to just compute the multiplication tables of these algebras, or what I like to call them cubles, because they're really not tables, they are tables of 3 arguments, so they are kind of cubic tables, so I call them cubles, whatever. So I compute the multiplication cubles, and then for example, we define in this case, we define the Boolean, the cubic set. What I call the cubic set is all the Boolean valued 2 by 2 by 2 arrays. So there are 256 such elements, which is just 8 elements, can be 0 or 1, so 256. And then what you do is you take any 3 of those 256 and you multiply them with each of the products, and you just compute the result is going to be one of those 256. And so you just write down computationally, just memory, you just store all the multiplication table. And so I'm in the process of doing this because it is very computationally expensive, apparently. I mean, when you try to do this, I mean, it's just arithmetic, but it takes a long time. It's easily parallelizable, trivially parallelizable. So it's very easy to make very efficient, but I just don't know how. So we can do this, but the point is not so much that it's difficult. The point is, once we have these things, for each dimension, so 2 by 2 by 2, 3 by 3 by 3, 4 by 4 by 4, for each of these dimensions, there's a single multiplication cubicle per product, right? The fish defines a cubicle. The Bhattacharya-Mesner defines a cubicle. The 3/4 Richards product satisfies a cubicle, right? And so the question is, how can you maybe tell them apart? If you just have the cubicle, which is this big, 256 by 256 by 256 table of zeros and ones, how can you tell them apart? Right? How can you, And so that's one approach. If anyone has any suggestions or any ideas on how to compare 256 cubed tables, I'm willing to listen. What is a good strategy there? Because that's the smallest one, because then you will have to do it for 3 by 3 by 3, which is much bigger, and so on. So that's one approach. That's the kind of numerical raw approach, where you just compute everything, and then once you have the final specimen of the computation, then you try to analyze it. The other approach is the kind of the complement of that, and then I go back to my presentation, which is, if you're looking for axioms of associativity, of n-ary associativity, you might wonder, how do you implement these axioms in the first place? So this is where I have the idea of what I call diagrammatic simplicity, which is sort of taking the complement of what I was saying before, which is literally computing every single case one by one. This is taking the most abstract sort of approach to what happens in matrix multiplication. So you can abstract matrix multiplication to be essentially this pattern, which a lot of people would recognize as morphism composition in a category, or the transitive closure of relations, or etc. So the way that you can extract the associativity axiom out of this kind of construction is if you label each of your edges FGH, and you apply that rule, but you keep the name of the label as consistent from the history of the rewrite, right? So if I apply the rule on the left, I will call this new edge FG because it comes from FG. And if I apply it on the right, I will call it GH because it comes from GH. And so the idea is that then apply the rule again, I get 2 edges between the same vertices, right? These vertices could be labeled 1, 2, 3, 4, right? So the names the IDs are kept. And so I get 2 edges between the same vertices. So one is called FGH, the other is called FG bracket H, the other is F bracket GH. So the statement of associativity is that indeed this should be a fully confluent system. So there's no ambiguity of how you express the final. So with that idea, you can actually extend. So this is what people call a semi-category, because it's just associativity. If you also want the unit property, that F composed with unit is F, or unit composed with F is F, you get that property. You can do it simply by writing that arrow F, then you add this rule, which whenever you find a vertex, you add an edge, and then you compose using the first rule, and then you now get 2 edges on the same pair of vertices again. And so by the same principle, you force these 2 to be equal. And that's exactly the equation of unit. So it's a principle that is very elegant. It works for a lot. So for example, dagger means reversing the order. So you have F, you reverse it, you get F dagger on the other direction, but you can reverse it again, and you get F dagger in the direction back, but you get the original F and F dagger both going in the same direction. So again, the same situation. 2 vertices, 2 edges, different names, the names should be the same. So you get the property of idempotency of involutions, right, of daggers. Similarly, if you combine daggers with composition, you can get the anti-homomorphism axiom, which is this idea that transpose or dagger permutes the order by this simple diagram. You have Fg. On the one hand, you can compose first and get simply Fg composed, or you can take daggers first. In fact, there are two steps there to just summarize it. And then you can here compose, or you can here take dagger. But in any case, you get a final state that is between the same vertices. One is called G dagger, F dagger, the other is called Fg dagger. Same principle applies, you make the names the same, you get that. So you can go on and you find a lot of things. You find operats, which are a bit more sophisticated categorical objects. Of course, you find semi-heaps, which is the big, quote-unquote, big discovery that we made. This is our main contribution to the field. The only result that I can claim to Richard, we did something, which is discover this particular result. So I was looking at your paper with Victor and Olga and Chitov, and you know, we had it on the table, and we had a fish diagram on the blackboard, and you know, my friend was saying, Xerxes was saying, hey, how do we understand this axiom? We knew that we wanted this axiom. This axiom was in your paper, and I was looking at the diagram, and I thought, wait, if I write this long fish, this 5 triangle fish, I can see that I see one fish swimming to the right. One fish swimming to the right, but then there's another fish swimming to the left, right? So the first pattern matches here, you get the tail, ABC. Second pattern matches here, you get the head, CDE. So these two are the ABCDE, ABCDE here, but then the middle one is swimming in the opposite direction, and because the labeling goes tail, body, head, it has to be reversed. Yeah. So then, you know, we found also this axiom. It was very elegant. So this, to me, is a very, it's a very powerful narrative, right? You begin with this very simple example of associativity, and then you find identities, then you find daggers, then you find operats, then you find semi-heaps. It seems very powerful. So the idea, so this was the paper. We call it heaps of fish, just to make the joke. So the idea is to really generalize this thing. So we call these things schemoids. I don't want to get too much into the specifics, but the idea of this, and we have it in Mathematica, is that you can computationally now write all possible initial states and see what states will lead you into confluent diagrams like the ones before. And then if you have such a situation, which is not trivial, because, I mean, only very special initial states are going to be confluent in this way, because most of them will just have several branches and won't get to a single confluent point. And the question is, okay, if I find such confluent systems, then I'm going to try to label things consistently in my first initial state, and then see what ambiguities I get at the bottom. So, for example, this diagram here, I don't think I have. Let me see if I have the notebook where I had this.
So the first step is ternary multiplication. It's clear.
Yes. So the first step.
Yeah, here. No, down.
Here. Yeah. No, but the steps goes from the top to the bottom.
Ah.
Yeah. So you begin with this. So this is your product actually, and applying your product, each of these triangles, right, is one of these products. Yeah. So if I operate this, I get this. If I operate this, I get this. If I operate this, I get this. Yeah. Right? And then I can still operate some, because there's some pattern there and some pattern there, and so on. The point is that at the end I get only 3, and then those I can operate and I get a final result. So if you look at what that formula is, I mean, it's kind of easy to see, but the formula that represents, if you notice, is that I have to write something that is the product of 3, multiplied with something that is the product of 3, multiplied with something that is the product of 3. So that looks like, A, B, C, X, Y, Z, P, W, U. Yeah. And then each of these is a hypermatrix, and you just multiply it together. So that formula is this down. And so you say, well, but it is confluent. Why doesn't it give you some interesting axiom? And it's a 9-element, right? If it is. So the problem is that the confluence of this diagram only corresponds to the freedom that you have to order the operation. You can first operate this, and then you will get this diagram, or you can first operate this, and you will get this diagram, or you can first operate this, and you will get this diagram. And then you have 2 things remaining, which you can then operate in whichever order you like. So what this diagram is telling you is that no matter the order that you choose to operate your brackets, you're going to get the same result in the end. But it's not telling you that there are two ambiguous ways in which you can operate your brackets, which is like the other axis before.
But inside the brackets, do you fix the elements?
Yes. So the elements are all fixed in the beginning here. I mean, it's just too small, but you will see like A, B, C, X, Y, Z, U, T, W, T, right? So it will all be fixed in the first diagram. And the confluence property of this rewrite system, of this directed graph, only tells you that there's a freedom in which order you operate your brackets. But it doesn't tell you that it should be associative. So this is just a cautionary example to tell you that confluence is not enough. You need confluence, but with something else. The something else is what I call overlap, which is could be understood as what Nick was saying yesterday about causal dependence.
Yeah.
So when you have the thing that is common to all these patterns before is that
algebras, associativity.
Yeah. So what is common to all this is that your initial state had overlapping matching patterns. So the three fishes. So it is true that there are three fishes in the first pattern, but not only that, they are overlapping. Right. The first fish is sort of overlapping the body and head is overlapping with the head and body of the second one, and so on. Right. And so every single pattern that you see in here, has overlapping patterns. Like, for example, here, the pattern there is overlapping the whole thing. So it's already mixed. When the second rule applies, it's applied to something that is already mapped. Here is one single thing, so it's overlapping to the whole thing. Same thing here, and here is the same, right? So in here, my pattern, which is this V shape, just two edges, one matches here, the other matches here. So G is an overlapping of both matches. So my hypothesis for the last couple of years has been, and we are still working on how to make this practical and operable. My hypothesis has been that you can define a property of rewrite systems that are simply defined in terms of pure edge rewriting that have very strong confluent, a stronger condition than just confluent. So they are confluent for sure, but they are also confluent in this special way in which the patterns are overlapping throughout, that will detect what we call associativity. And so my strategy to find the associativity of these products is to write take the product, write the Plex diagram, so write the triangles or whatever, and then try to search for these kinds of rewrite processes. So far, we found none. So far, we haven't done extensive searches, but we know, for example, that if you want to up to 9 elements, right? Up to 9 elements involving 9 axioms involving 9 elements. There are, so you might be wondering, how many initial hypergraphs are there that you can, of this kind? In the last slide, how many hypergraphs of this kind involving 9 triangles are there? So these are simple connected, right? So there are 12,500,000 such hypergraphs. So there's a lot of them, right? And so the idea is that if there are any properties that, like associativity, that involve at least 9, or I mean at most 9 elements, they are going to be represented by a pair of an initial state with at most 9 triangles and a choice of rewrite rule. The problem is that rewrite rules, we really don't have that many. We have like 3 or 4. We have the Bhattacharya-Mesner, the fish, the 3 fours, and so on. But initial states, we have 12 million. Right? And so we could, I mean, this is a manageable size. The 12 million is manageable. Generating these 12 million hypergraphs is not that difficult. But knowing exactly what to search in the rewrite systems that they are generated, that's not so trivial. I mean, that's why we've been sort of like, I've been talking to Nick and to Nicholas Baer, that he presented yesterday, and we are trying to figure out what are good criteria to navigate this very big computational space.
And we don't find anything in the confluency related. I mean, people have been probably using confluency properties in other systems, no?
Yeah, the problem is that our system is like we need those results for exactly the system. Otherwise, we
Yeah,
can't
I
do
know it's
anything.
not enough, but maybe there are, okay. So
Yeah, so these techniques are super relevant, but they need to be applied exactly to the system for it to generate any meaningful answer for our question. Because the question is not about this system. The question is it's a related question in purely algebraic terms. This diagram is just a guide to allow you to discover there. So in order to get any meaningful answer for the algebraic question, you need to apply those techniques exactly to the system. So if, which in my opinion, kind of reduce to the same question, because you will give, Nick will take the rule and he will find the rule algebra out of it. And in the process, he will find all the overlaps. So if he does it correctly, he will probably find what we are looking for. My worry is that the rule algebra that he works with is binary. So it means that you only really need to look at overlaps of the pattern with itself once, or 3 times. So, 3 times might be enough for this because that seems like the right cardinality. But the point is that
what do you mean once? So do you do like FGH equals FGH with brackets moved, or what do you mean once?
Once meaning the number of nestings that you allow. So applying once means that you only have one bracket.
Yeah.
Applying twice, it means I have one nested into another 3 times and so on.
Not this one.
That is 4 times, right? Because it's one big bracket and 3 inside. So their results will. I think the thing is that my understanding, and if Nick watches this or gets some air from what we're saying here, I think we are just studying a rewrite system primitively, right? We are not using rewriting as a technique in some other study. Our question is really, this rewrite system, how does it behave? So absolutely, their techniques are going to be relevant because they have, they study abstract rewrite systems, so it's absolutely relevant. But in a sense, they will only be relevant when they are applied literally to this case. In which case, if they produce something like a result that I might want to hear, like there are no such confluent systems in your 12,500,000 set of hypergraphs, then that's an interesting result, because then it really is a full confirmation that you should not expect axioms of this kind. But anyway, that's kind of the point of the talk. Many of you already know this, but all my findings and my collaborations are on this page, ret.science. You can find my papers there. But that's all I wanted to say. Thank you very much. So,
until I forget.
Yes.
There's something that I remember now, that Jacobi identity for ordinary Lie group
Algebra
is derived from associativity of the Lie group.
Yes.
I don't remember exactly if it's in Ponomarenko's book, and you just define the Lie group, and they mention a group with n coordinates, and then a new element is given by n functions of n coordinates.
Yes.
So this n functions of n coordinates, suppose that now you make another product, we get iteration, then you require that associativity. And somehow, when you differentiate it, at the end,
you get Jacobi.
You get the Jacobi.
Yes.
So now, if maybe we could approach the associativity in algebra, but no, sorry. The algebra is not associated.
No.
But the Jacobi identity comes
from associativity. Yes.
So maybe the general Jacobi identity would come from associativity in any group.
Exactly.
But how to define
n-ary associativity? Group, yes, exactly. That was my question, yes.
What is in usual groups, the central thing is the unit element.
Sure.
Once you have unit element, you have inverse, and so in n-ary, so you have to, I don't know, either you have two unit elements that come together and they reproduce. Then is it possible to have a unique inverse?
So
You have two inverses.
Yes.
Because you have first and second unit. And I don't know, but I think it has to encompass ternary group.
So yeah,
Group.
yes, group, yes. Groups. So there is literature on what have been called this is I think some Polish authors on can't remember. The name is escaping right now, but there is a fair amount of literature on what having called p-adic groups or n-ary groups. But a simple check that you can do is if you take a p-adic group in this sense and you try to compute the infinitesimal component, or if you take a p-adic associative algebra and you try to define the commutator or something like that, you will find that you don't get.
But p-adic is on p-adic numbers.
No. So p-adic is the historical name. It means n-ary. N-ary, yeah. It's n-ary. The n-ary groups. Dudek is the name.
Yeah.
Dudek. Yes. Dudek is the name. Yes. So they do n-ary groups, which assume n-ary associativity, and n-ary associativity really means that you have an n bracket and you can move it in any sequential direction. But they also do weak n-ary groups, meaning that you don't assume some of the associations of the bracket, and then you assume some permutations and whatnot. So in all that literature, there's no construction that taken that and made infinitesimal, or taken that as an algebra and made a commutator out of it, gives you a Jacobi, a generalized Jacobi. It just doesn't work.
Yeah.
So it's a valid theory. There's nothing wrong with it. In fact, there are some results that are interesting.
No, going to infinitesimal should give you something.
It should give you something, I agree, but it's not.
Something is not a Jacobi.
It's not a Jacobi identity. Yeah, it's interesting. Yeah, but yeah, going to infinitesimal is interesting. So actually, what I mentioned on Monday about the bi-units in semi-heaps, that could be an interesting. I didn't follow up, but it could be an interesting exercise.
Yeah, I'm sorry. I think I understand why it's difficult to go to infinitesimals, because going to infinitesimals in the usual group means that you have the unit element.
Yes.
And from this unit element, you just go. I needed two unit elements. Really? How do you...
Well, that's one way to see it. Another way to see it is to think about invariant vector fields.
Yeah.
So one way to see the Lie algebra is that it's the tangent space at the identity. That's one perspective. Another perspective is that it is a finite dimensional Lie algebra of the Lie algebra of vector fields generated by the left invariant vector fields. Right, and the left invariant vector fields are simply the vector fields that are equivariant with respect to the left action of the group on itself.
Yeah.
Right. So if you have an analog of an action in your object, you can define the whatever invariant vector fields or whatever invariant bivector fields. So my guess is that the analog of the infinitesimal analog of these kinds of things in the ternary smooth manifold with a ternary operation. I'm not assuming it's a group. It's just smooth manifold with a ternary smooth operation.
Yeah.
I'm not assuming any associativity. The analog of an infinitesimal vector field would be an infinitesimal bivector field, because you would have, you fix one entry for the action, and then you have two entries left. So in the binary case, you have only one entry left, which is where you put your one parameter group. Here you have two parameters. So two parameters span a surface. So that's a bivector infinitesimally.
Okay.
So in fact, I actually had a formula that was similar to the formula. You know this paper, Chinese paper, where they find the Jacobi identity with a combination of traces and products? There's a paper. I should find it. It's not very interesting in my opinion, because it basically just concoct this product where I think it looks like looks something like this. It looks like you have A, B, C, and you trace of A times bracket of BC plus, and then cycling, right?
Yeah.
Trace B, A, right?
Yeah.
So it looks something like this. And I think that satisfies Jacobian. So, but I never made anything of it because it is binary. Sorry, it's made of matrices, so it doesn't really give me anything ternary. It basically built this Jacobi ternary Jacobi.
It's kind of it gets you completely out because
Yes.
See the bracket. This is ordinary bracket.
This is ordinary matrices and ordinary brackets.
So the bracket is always traces.
Yes.
So usually, for example, the algebras, mostly of the time when they're represented by matrices, these matrices are traces. But if you work on traces matrices, you get 0, 0, 0.
Yeah, but so the claim is
These matrices are traces.
Yeah. But no, but these matrices are generic. The claim is that the claim is
how the traces. Matrices are generic, but then you project go into traces.
Sure.
So if you iterate it, what do you get?
You mean that it has no physical meaning for you?
What, traces?
No, what they form, what they define.
No, I'm looking at algebraic.
Yeah.
If these are whatever matrices, if these are matrices,
So the derived algebra is already 0.
Yes. Are also matrices, but they are traces by definition. Because the trace of a product does not depend on the order. So the trace of BC is the same as the trace of CB. So the trace of the CB is 0. But here you have not yet took the trace. You didn't take the trace, you take only the trace of this generic matrix. Okay, first step it works. But now this result is a traceless matrix. So if you continue, you cannot continue with it.
Yeah.
It's over. The game over. Because if you try to apply the same formula next time to the result, it gives you nothing. There's kind of nilpotent thing. No extension. You take first any matrices, you formulate this is very good, but how you get Jacobi, I cannot understand. Because in order to get Jacobi, you have to iterate again, right?
This might. I'm trying to find a paper where they define this bracket. No, I don't think it was this one. I remember it was. Here we go. I think it's this one.
So, can I say, do you hear me?
Oh, yes, Victor.
I remember that you mean the ternary algebra where the ternary commutator was constructed by trace and commutator of two matrices.
Yes.
This was a paper. This was a paper of physicists published. I don't remember the names. Maybe
I think I found it. I think I have it on the screen. I think they define at some point down here. I think they define this bracket, but no, wait, it should be in the beginning. .1. So in this paper, they're claiming that this particular product, ABC, which is it? IJP. Oh, that's the fish. Interesting. No, it's not efficient. What is that? P?
Can you zoom in?
Sure. Oh, I couldn't see it. Yeah, sorry. That's the product. They claim that the skew-symmetric bracket satisfies the Jacobi identity 3.1, which 3.1 is here. Oh yeah, the correct one. Yeah. This is the, that's my Jacobi identity. So okay, so interesting. So this is why I remember. This is a good, interesting exercise. So this is the product. So this is a live code with the ijk p, and then q. So there's j is repeated over, and it doesn't sum. So and b sums. So I have something that looks like this. Okay, this is contracted, and then b is connected to q and m, which is just over here. It's not connected to anything.
Yeah.
So b has looks kind of like this. It's all contracted.
And B13?
No. They can see now. So this product really is a binary product of cubic matrices. So it basically looks like this in a sense, because okay, let's understand.
It's
Right.
really true because this last one is connected to the first one.
Yeah, A, C, and B. B is unconnected. Q and M are not shared with any other matrix. So it really looks like this. So B is a trace. So you trace two indices twice. This is Q, and this is M. Right? So it just becomes a number. You can multiply a number by a hypergraph in this system. And then what you do with these two is this. You have three indices, I, J, K. But this operation here really is matrix multiplication. Because you can see P and B appears only in one. So basically you have IJ, these are kind of multi-indices. So there's another paper where they explicitly recover this. I think, I believe this product can be derived from this product. Because if you think about it, this trace here, this parameterization, they have to symmetrize it in the end. But yes, I think I don't have a proof, but basically the trace here will look like this sum, QQ. Okay, that's the trace. And then this thing here will look like B times C, but after you fully antisymmetrize, you would get minus BC, and then you will get the commutator at some point. So
it's not a problem that it wants a weird structure, which is kind of a number and
it is a problem in the sense that
it's not.
Yeah, it's a problem in that this is not a ternary operation. I mean, it defines a ternary operation as a whole.
Well, it is in ternary operations. That's how you define a ternary.
I mean, it is ternary in the whole, but it's a composite of a unary and a binary, which is also explicitly here. This is a binary operation, right? It's a number. Well, I mean, binary. It's a modular operation. It's binary. Number times matrix.
Yeah.
And then this is matrix with matrix, and this is matrix with number. So it's binary, unary.
So in a way, then it's kind of like a generalization, very specific case where it's semi-ternary because it's function of one element which is separate in the trace. Yeah.
Yeah, it's similar to why I was saying yesterday or 2 days ago that when you have a field of ABC, right? Mm-hmm. You can reinterpret ABC as matrices, with multi-indices, and it really becomes A times B transpose times C. So although fish in a whole is ternary, it is a composite of binaries and the unary. Transpose is a unary. From 1 gives you 1. Product is binary. From 2 gives you 1. As a whole, you can compose it and you get a ternary. But that's like saying when I have a binary, I can just make a composite and I have a ternary. Sure. But that's a composite binary, right? It is made of 2 binaries. And the result that we showed earlier is that none of the products that we are interested in, the fish, Richard's product, the Bhattacharya-Mesner, they cannot be written as a composite of binaries or unaries or anything. So on the one hand, it is interesting that they find the Jacobi identity in this particular product. But in my opinion, they find the Jacobi identity by having some kind of hack of the binary Jacobi. Because, I mean, the binary Jacobi is here.
May I just make
yes.
Because they cannot be made up of binaries of the same dimension.
Yes.
But I'm sure that if you go to some very big dimension,
then
you get something and then they will, it's like other field.
Yeah, that's
Diagrammatic is in developing algebra, very big one, which you can pick any institute, they will give you, but the price to pay that you have many other elements you did not know what to do with it. Just do it.
Yes. I was trying to find, because there was a paper that, for sure, I don't know if it was this one.
Break to go to see the director.
Yes, we can have a break now. Let me see if Josh is online.
Yes.
No, Josh is not. Victor, do you have any questions, any comments at this point?
Start with the next talk in how many minutes?
No, at this point, no.
Okay. Well, as soon as he joins. Because it's.
I'm going just to.
Shall we write?
He's sleeping.
Right?
He's asleep. As soon as he wakes up, he will join. So.
Nice.
I will be in my office.
Okay. Yeah, we will reconvene as soon as Josh is here, probably in about 30 minutes. Thanks.
Yes, thank you very much. Then maybe I will write in the chat that people can.
Say it again, James. Oh, Josh is here.
Nice. Hi, Josh. Good morning.
Maybe you can turn on your camera so you can see you.
Yes.
And actually your microphone as well. Hello, Josh.
Hi, Carlos. Can you hear me?
Yes.
Hi.
So we're all in the same room, although you can tell, but...
Richard just left.
So we're going to have about a 20-minute break.
So you have a time for coffee and us too, probably.
Yes.
Okay.
I just finished my talk. We had a longer break in today's schedule because we had a gap and the speaker couldn't come in the end, unfortunately. So about 20 minutes or maybe at the top of the hour, we'll resume here.
Okay, great. That sounds good.
Top of the hour.
Yeah.
Depends for every person in their time zone.
Okay. All right. Yeah, I'll make some coffee and be back then.
Well,
Perfect.
Okay.
You know
Great.
it, Josh. Let me just move the computer to the other side.
Josh, you can share your screen if you want.
Yeah, 1 second.
Perfect.
Okay, do you see everything?
Okay, now we do. Sorry, the logistics here are not trivial, but yeah. Yes, I think we are all ready to go. James, is everything okay on our end? Perfect. So thank you very much, everyone. Welcome to the final session of the Hypermatrix workshop. I just wanted to make a couple of small announcements or comments before we proceed with the final presentation. Remember that we are hosting this online at the Wolfram Institute. We have an online community. Everyone is welcome to join our Discord. James maybe can share the link on the YouTube live stream if in case we have any viewers there. Many of them probably are very familiar with us. The other link that I want to share is if you go, for anyone here on the call, if you go to this link, if I can get the chat, you can see a Discord link over there. You will find our Discord server where we have specific channels designated for this workshop in particular. So any information like slides and links that were shared during the live streams will be put there. And of course, any follow-up discussions will be also hosted there. Also, the second thing I wanted to say before proceeding is that I'm extremely thankful to both Lyubov, who is here on my left, you can see, and Richard, who's just behind me, for hosting this event here. It's very, very inspiring to finally be doing things on site. And yeah, thank you everyone for, also Josh and all the speakers for joining from various locations and trying to make your schedules compatible and so on. It was really nice. So yeah, looking forward to what you had to say, Josh, and take it away.
Great, thanks. Can you hear me all right?
All good.
Great, okay. Yes, yeah, and thanks to the organizers for organizing. Yes, I'm sorry I wasn't able to join live the previous days, but I was following on video. And so I've been there in spirit, and it's been a very nice workshop. Yeah, yeah, what I wanted to tell you about today is a connection between a hypermatrix tensor thing, which I guess Carlos talked about in his talk, the Bhattacharya-Mesner product, and the graph isomorphism problem in algorithms and complexity, and in particular the Weisfeiler-Leman algorithm for graph isomorphism. So this is very much work in progress. This is sort of something that I only realized sort of as a side thought in conversations with Carlos, I don't know, a few weeks ago maybe. And I've had a few more thoughts since then, but it sort of pulls together threads from different areas. And so I want to explain what all those are and yeah, pull them all together. And I really do hope this will be educational and interactive. So please do stop me if you have questions. All right, so we start with the Bhattacharya-Mesner product. And just to set notation, so I'll write if I have an nth order hypermatrix, I'll usually denote that by T, and that means it has, when I say nth order, for me, that means it has n indices here. And I'll say it has format d1 by d2 by by dn if the jth index can take on dj different values. So these are, if you're thinking of this as a box, say a third order tensor, the di's are the side lengths of the box. So this might be d1, d2, d3, for example. Okay. All right, so that's just setting notation. And now we come to the Bhattacharya-Mesner product. So you're given n many, so I have T1 up to Tn, nth order hypermatrices whose formats look like this. And the thing to notice about these formats is that they all share one common side length, but in different indices. And you might imagine that's the one we're gonna sum over in a second. And then in the other side lengths, they have to match up. So for example, you see in this first index, aside from the first one, which has to have this common index capital D, they all have the same length. Okay, and then similarly in the, if I look in the third index, all of them except for that one that has the capital D, they all have the same length D3. Okay. So if you have that, you can then get out a new nth order hypermatrix, and that new nth order hypermatrix is defined by this formula here. So, and I left these things out so that I could write them so you can see as I write them, because otherwise you get lost in the indices. So it's going to be some, we're going to do some sort of contraction, partial contraction, and it's going to involve all of T1 up to Tn, and from T1 we're going to sum over this first index. So L is, L here is this index we're summing over. So we're going to sum over that first index, and then it will just have whatever these other indices are. And so notice these indices are the indices of the output. Okay. And then the second one, its first index is going to be whatever the index of the output is. The second index is going to be the one we sum over. The third index will be the index of the output, and so on. And then in the last one, all of them up to the second to last one will be the index of the output, and we'll sum over that last one. So just to highlight where we're summing here. Okay, and right, to sort of match the highlights with what I did above, right, these are all that first leg, and for example, these are all that third leg. Okay, and I'll denote this with this brackets, T1 up to Tn. Okay, so T1 up to Tn are n many nth order hypermatrices, and when you take their Bhattacharya-Mesner product, you get a new nth order hypermatrix. Okay, so when you do it with capital N, it can be confusing because your indices have indices. So I also wanted to do it just for 3, where my indices can be ijk. And the notation here, I saw Carlos flashing his slides earlier. The order is slightly different than what he had, but it's like isomorphic to what he had before. So, right. So we're going to be summing over this L. And so we're going to go L, J, K for the first one. In the second one, we're going to sum over the second index. And then the third one, we're going to sum over the third index. Okay, and then I just fill in these other things according to what the index of the output is. So if I'm looking at the ijk index of the output, then in the second one, I will have I, L, which I'm summing over, K. And then the third one, I will have I, J, L, which I'm summing over. Okay, so, okay. All right, and then, so that's the product. And by a Bhattacharya-Mesner algebra, I'm going to mean a subspace, and it's going to be important for me later that it's actually a subspace of nth order hypermatrices that's closed under the Bhattacharya-Mesner product. So if you have nth order hypermatrices in your subspace and you take their Bhattacharya-Mesner product, that should also be in the subspace. So it's closed under, by being a subspace, that means it's also closed under linear combinations, right? So we have sort of two operations here. We have linear combinations and we have Bhattacharya-Mesner. Okay. And this is a good point to pause because we're about to shift gears. So the question is, yeah, so are there questions at this point? And I can't see the chat.
Yeah, I think there are no questions, but maybe just a point to emphasize that for n equals 2, of course, we have matrix multiplication.
Oh, yes. Right. Excellent point. Yeah. Yeah, so actually maybe let me do that over here.
I mean, matrix multiplication is one example, but it can be also some weird ones.
Sorry, what was the question?
No, I think, I mean, if you're speaking to just speaking.
No, but it just was saying that there can be two types of already for 2x2 case, right? You can get two types of multiplication.
No, only one.
Well,
oh yes.
In this notation specifically.
Yeah. Okay. Right. So yeah, right. So for n equals 2, right, actually the way I've done it, I've done my indices sort of backwards compared to usual matrix multiplication. But it's like isomorphic to matrix multiplication. So for 2, T1 and T2 are now matrices. And if I look at the IJ entry here, the way I'm writing things, this is the sum over L of T1 LJ T2 I L. Okay, but you can see this is basically sort of, I've multiplied my matrices in the opposite order, right? So this is the same as T2 T1, the ordinary matrix multiplication, the IJ entry. Right. Yeah. So it's like isomorphic to matrix multiplication.
Okay.
Okay. Other comments, questions at this point?
No, I think we're good to go.
Okay, great. All right. So now this is my talk outline here. So what I've done so far is we sort of started in the parking lot and we walked up this little path to this vista. This is like you are here. And I've shown you the Bhattacharya-Mesner product and algebra. Okay, but now we basically have to go back to the parking lot, unfortunately, and sort of start over from the beginning and take a longer walk to connect the other topics we want. So first I'm going to tell you about the graph isomorphism problem and just sort of some background on that. And then we'll get to the Weisfeiler-Leman algorithm for graph isomorphism. Okay, and then finally, we will walk down this path and we will come across this bridge, and really, this bridge is really what this talk is about. Is connecting Weisfeiler-Leman back to Bhattacharya-Mesner. Okay, so graph isomorphism. When computer scientists talk about the graph isomorphism problem, they mean the algorithmic problem. So we're trying to find efficient algorithms for this problem. So the input to your algorithm is two graphs G and H, and they can kind of be given to you however you want, but like you could imagine they're given to you by adjacency matrices. And the goal is to find either to compute an isomorphism between them. And for those of you who don't know or don't remember, I'll say what that is in a second. So the goal is to either find an isomorphism between them, if it exists, or to say they're not isomorphic. So an isomorphism of graphs here is a function from the vertices of one graph to the vertices of the other. That's a bijection. And it has the property that uv is an edge of the first graph if and only if f of u, f of v is an edge of the second graph. Okay, so now we have some participant interaction here. So are these graphs isomorphic, and why or why not? Okay, I'll give you the spoiler. They're not isomorphic, right? Okay, but why? Right? Why is it that any bijection from this one to this one, from the vertices of this one to the vertices of this one, cannot have this property that it maps edges to edges and non-edges to non-edges?
There is no edge, right? There are not enough edges, first of all.
Right, there are not enough edges. Okay, good. So counting edges, right? Okay.
It is not enough.
Right, so right, that's right. Very good. Yeah, right. So, these are finite graphs. Everything I do is for this talk is going to be finite graphs. And so indeed you can count edges. And this condition implies that the number of edges of G and H is the same, right? And here they're not. Here you have 2 and here you have 3. Okay, now, what about these graphs? These graphs now, I promise you, if I wrote this correctly, they have the same number of vertices and the same number of edges. So the question is, are they isomorphic? And if not, which they're not, why not? Like what can you see about them where you could prove to me that these are not isomorphic?
That the number of, if you locate yourself in the central vertex, right?
Mm-hmm.
The number of matches for one graph and the other won't be the same, right? With the unique other vertices.
Right. So, right. What Carlos is saying, or maybe I can try and rephrase this. If you suppose there is an isomorphism, so you ask where does this central vertex go? Okay. And visually, I've kind of set it up where like you want the central vertex to go to the central vertex, but you also need that, right? This central vertex has 6 neighbors. Okay. And so you can't send it here because this only has 1 neighbor, right? And similarly, you can't send it anywhere else. You can't even send it here because this only has 5 neighbors, right? So here we have this sort of local invariant where this is a degree 6 vertex, this is degree 5, and actually, it's not just that that's degree 5, it's that in this other graph, there are no degree 6 vertices.
Yeah.
Right, so here, okay, so here, for this first one, our isomorphism invariant was just number of edges. Okay, and for the second one, our isomorphism invariant is really, in this case, the set of degrees, right? And we just see that in this first graph, it has a 6, right? And it has 6 vertices of degree 1. And in the second graph, it's different, right? It has only 5 vertices of degree 1, a vertex of degree 5, and a vertex of degree 2, so things don't match up, right? And when I say isomorphism invariant here, what that means is any 2 graphs that are isomorphic must have this being the same.
Mm-hmm.
Okay, so now our last example, and I need to finish drawing it here purposefully so that you can sort of spot the difference. So they start out the same, and then I'm going to add triangles to these, but I'm adding them in sort of different places. Okay, and I claim to you that these are not isomorphic, and the question is, can you tell that? Can you prove that back to me, right? What can you see about these graphs? So now the number of vertices is the same, the number of edges is the same, and the set of degrees is the same. Right? Even the multi-set of degrees, if I count how many vertices there are of each degree in these graphs, it's the same. So the question is, can you prove to me, how can you prove to me that these two are not isomorphic?
Well, then you can go kind of even higher order than the degrees, right? You can go kind of on the motifs or like ensembles of this.
Right. So you could look at
go
yeah, go ahead.
Combinations.
Yeah. So okay, if you look at say subgraphs, if you look at only small subgraphs, you kind of can't tell them apart yet because both of them have 3 triangles. You know, even if you count, say, like the number of subgraphs that look like a triangle with an edge off of it, those are actually the same in both of these graphs, right? And if you look at things like, say, paths, actually, I think in these graphs, paths of almost any length, I think, have the same count. Okay, so the question is, you know, okay, so this is a good idea, but like, can you actually do it in these graphs? Can you point out to me, you know, exactly why they're not isomorphic?
So I would say something. I mean, I don't know, naively, that I can find different subgraphs in each of them. Right? If I specify a subgraph that is 2 triangles with and joined by 1 vertex, I can find it on the right, and 2 triangles with 2 vertices, I can only find it on the left, right?
Right. Okay, yeah. Good. So here we're saying.
No.
Sorry, what?
No, but because if you will find at least one motif, which is the weirdest one, which is not present in the other one, is it what you were saying? Right? Like there is the longest motif over there, and it's not present there, right? It consists like of this snake.
Well, it's just 2 different subgraphs.
Mm-hmm.
Yes, right. Yeah. So same thing. So so here, when we were looking at degree, that's kind of looking very locally at a vertex. And here we're saying, look at motifs or subgraphs. And if you get big enough, you can find they're sort of all over the place. They'll be different. But one of them that Carlos was pointing out is if you look at this one, this is a graph with 2 triangles connected by a path of length 2. And that just doesn't exist in this graph.
Mm-hmm.
Right? Okay. But that's kind of complicated. Right? So I claim actually, by just looking at degrees, not just the set of degrees, but slightly more information about the degrees, you can actually tell these 2 apart. Okay, so first, I'm going to label everything by its degree. Oh, oops. That's not degree 1.
Yeah.
That is also degree 3. Okay, good. All right, so the sets of degrees match. Okay, but now what I'm going to do is I'm going to treat the degrees as though they were colors. So we have 3 colors here, 1, 2, and 3. And now what I'm going to do is I'm going to recolor things based on the colors of their neighbors.
Yeah.
So, for example, I'm going to run out of colors pretty quick here. I might color this. This color is going to mean vertex of degree 3, which has 2 neighbors of degree 2 and 1 of degree 1. So degree 3 with neighbor degrees 2, 2, 3.
Mm-hmm.
Okay. And so I can now go through and I can say, well, where else do I see vertices of degree 3 whose neighbors degrees are 2, 2, and 3? I see it here. I see it here. And that's it. Right? If I'm looking for a vertex of degree 3 whose neighboring degrees are 2, 2, and 3, in this graph, there are 2 of those. And in this graph, there's only 1. Okay. So this was like, I didn't quite have to go to motifs or subgraphs, right? You could, but you didn't actually have to. You just had to pay attention to a little bit more information about the degrees. Okay. And this leads us to the Weisfeiler-Leman algorithm. Okay, so before we get there, just a comment about sort of what is the state of the art of graph isomorphism and a bit of the history. So this, the problem actually goes back to sort of at least the foundings of computational complexity. There were two independent papers on opposite sides of the Iron Curtain that both defined NP completeness. And in both of those papers, they ask about the complexity of graph isomorphism and left it as an open problem, which is still open today. So the state of the art today is you can tell whether two n vertex graphs are isomorphic in n to the log squared n steps. This was a major breakthrough by Babai a few years ago. And in practice, it is essentially solved. It's like mostly solved, but by simpler methods. And the simpler methods are sort of like the ones used above. But actually, one thing I want to highlight is in both of these, sort of the best we know in theory and the best we know in practice, both of these use these sort of coloring ideas that go back to Weisfeiler and Leman as crucial ingredients. So Babai's algorithm is not just Weisfeiler-Leman, but it uses Weisfeiler-Leman over and over again as a subroutine. Okay, and the practical software for solving graph isomorphism definitely does this kind of naive, what's called naive vertex refinement, where you color by degree and then you sort of go through this process. Okay, so now what I want to do is I want to take you through, I want to formalize this process a bit and then connect it back to some algebra and eventually algebra of hypermatrices. Okay, let's see. And when did we start and how am I doing on time? Or maybe when am I supposed to end?
Basically, you started at 1/4 or so you have like, you went for 20 minutes or so.
Okay, perfect. Okay. All right, so now we come to formalizing a little bit what we just did. So the idea here is with what's called vertex refinement, which is sort of a one-dimensional version of Weisfeiler-Leman. The Weisfeiler-Leman algorithm is actually a family of algorithms that's parametrized by a dimension. What we're going to do is we're going to color the vertices. And actually, initially, we can just say, I'm going to give them all the same color. So I just call it 1, whatever, I just need a name for it. Okay. And then what I'm going to do is I'm going to refine the coloring. So if I have my coloring at time t-1, chi sub t-1, the color of a vertex v at time t is going to consist of a pair, 2 parts, consisting of its old color. So this makes sure like I'm not forgetting any of the previous information. And then the multiset of the colors of its neighbors from the previous coloring, right? So this is the multiset of chi sub t-1 of the neighbors of that vertex. Okay, so after one step, right? So initially, everything has the same color. It's not distinguishing any vertices. After one step, this part, so let's look at what chi1 looks like here. This looks like chi0 of v, and then the multiset of its neighbors degrees. Okay, chi0 of v, though, this is just 1. Okay, and what is the multiset of its neighbors' colors? Well, all of its neighbors currently have color 1. So this multiset is just telling you how many neighbors it has. Right, so this is just a multiset of 1 repeated degree of v many times. Okay, so after one step of refinement, this chi1, our first coloring, gives us the degrees. And then after 2 steps of refinement, it gives us, well, more refined information, right? It's essentially doing this, right? After 2 steps, it's saying, what is my degree and what is the multiset of my neighbor degrees? Okay. And so at each stage, this coloring partitions the vertex set into what I'll call color classes, and I'll denote those gamma sub t(c), where t is the depth of the iteration we're at, and c is the color class, and that will just be the set of vertices that have that color at that time. Okay. And because we've done this, because the color at the previous time step is part of the color at the next time step, that guarantees that this partition, as you go from time t-1 to time t, it's always getting refined, right? You're breaking these color classes into, they either stay the same or it breaks up into smaller color classes. Okay. And because everything is finite, eventually that breaking process has to stop. It either stops when everything is in a singleton color class, or when, because of the refinement and the structure of the graph, the partition just doesn't change after you do refinement. You get back the same partition you started with. Okay, and at that point, we say the refinement stabilizes. Oh, yeah.
Josh, can I ask something?
Yeah.
I mean, it's just more a technicality of the multiset part of it. But so, is it true that the chi t-1 of u in the formula for chi t of v there, do you have the, I mean, is this taking basically the multiset of the whole thing in the next step? Or, okay, I'm just a little bit confused about the fact that there's a pair and then the multiset inside.
Oh, right. Okay, so you can think of it that way, that
Okay.
like, okay, at time t, what is this? This is a multiset of pairs where each pair in there consists of a thing and a multiset of pairs and Okay.
Yeah.
In practice and in algorithms, what you do is at every step, you have your coloring and you have colors and you usually just make them numbers. Like if you're
Yeah.
writing an algorithm, say the colors are like 1 up to C.
Yeah.
You compute this, and then, so you compute that for the next step. Okay. And then you see, okay, what are all the distinct pairs like this that I see? And I just assign each of those pairs a number, a new number, 1 up to some C prime.
Okay.
So like you can kind of forget about that iterated structure.
see.
When you want to think about this, sometimes it's useful to remember the iterated structure, but sometimes it's not. Like a lot of times you just care about this partition.
I see.
Yeah.
But would it work? I mean, I'm just curious. Would it work if I had a multiset around the whole thing? So instead of brackets, just the whole thing.
Okay, for this part, I think it's important that it's a pair because you really want to keep. Okay, let me say naively.
Yeah.
I think you really want to keep your previous color separate from your other stuff.
Okay.
Like you really want to know for, what's for the color of the vertex V, you want to know what its color was previously.
Right.
Okay, the reason I hesitated is because actually there are many different variants of Weisfeiler-Leman, and a lot of them end up being equivalent in the sense that one variant will distinguish two graphs from one another if and only if the other variant does.
Right.
And so if you made this whole thing a multiset, where like instead of a pair like this, you just said I had the multiset and I'm going to include the color of V in this multiset.
Yeah.
Is that equivalent in power to what I've written here? Maybe, but it's not
Right.
obvious to me. Yeah.
Right. Okay. Yeah. That was thanks. That was the point.
Yeah. Okay.
And it doesn't matter, sorry for question. So you kind of say that you started as an iterative process. I mean, you didn't say iterative, but you can consider it as an iterative process?
Yes.
In principle? Okay.
Yeah. What do you mean, does it matter? Like, yes, I think of it as an iterative process.
Yeah, no, but I'm just trying to kind of imagine how I would compute that, or like, if there would be any things where there would be contradictions, or I would need to resolve it because we discussed it.
Oh, I see.
Today.
I don't think so. We'll do an example.
Yeah, I think it's about the locality also of this property. Maybe.
Yeah. Okay. All right. Other questions? Okay, great. All right. So because we've done this, where we have this pair and the pair includes the old color, that ensures that our partition only ever gets finer. And that means eventually this has to stop. This process has to, the partitions have to stop changing at some time t. right? The color itself might change because it has this sort of nested structure of whatever, but the partition you get into these color classes eventually has to stop changing. And that's when we say the refinement has stabilized. And when that happens, we often denote that chi sub infinity, but really that's just chi t for t sufficiently large that you've stabilized.
Yeah.
Okay. All right. So, right. One thing we can do is,
and that, Josh, just to clarify, to double check,
yeah.
That's a vertex partition, right?
Right. This is a partition of the vertices. That's right.
Yes.
Yeah. Okay. We're going to generalize that in a few minutes, but
okay.
Yeah. Okay. Let me see how we're doing that. Okay. Right. So, yeah, we can go back here and do one of these examples. I think I want to do this second example. Yeah. Okay. So in this example, okay, I've already done the coloring by degree, which is our chi sub 1, right? Okay, and you see in our chi sub 1 coloring, we see there are 5 vertices of degree 1 in this graph. Okay, over here, it's actually already stabilized. It's not too hard to see because every vertex, a vertex has degree 1, if and only if it has degree 1 and it has exactly one neighbor of degree 6. So the color class of vertices of degree 1 here isn't going to change when you refine your coloring. And same with degree 6. There's only one vertex of degree 6 and it has 6 neighbors of degree 1. And when you refine, you will just get back, this is the only vertex in its color class. Okay. But over here, some refinement can happen because here we have 5 vertices of degree 1, but they are not all the same. One of them is not like the others, right? So if I do my next round of coloring, what I will find is these 4 all have degree 1 and have one neighbor of degree 5. Okay, but this one has degree 1 and has a neighbor of degree 2. So it gets a different color. Okay, and then the 5 and the 2 are already in their own color classes because they're the only vertices of their degree. Okay, and so this graph, this took 2 rounds of this iteration to stabilize, and now I claim this is the stable coloring. Okay, where you think of if 5 and 2 are their own colors, so give them colors. Okay.
Yeah.
All right. You could do a similar thing here, and it takes longer. Yeah. But one of the things that you will see when you do that is that this vertex, right? This is the only vertex of degree 3 with 2 neighbors of degree 3 in both of these graphs. Okay, and so this one is going to get its own color. And then what's going to happen is that color is going to propagate a little bit because this vertex is the only vertex of degree 1, which is adjacent to the special vertex. And this vertex is the only vertex of degree 1, which is not adjacent to the special vertex. Okay, so the coloring here, it is more complicated, but it's the same process. Okay, so questions about this process, and now we're going to see an algebraic version of this next. So questions about this?
I think it's okay.
Okay, great. All right, so now what I want to do is sort of an algebraic view of vertex refinement, and in some sense, this part is like implicit in work going back to the 1960s. But actually, they did the 2-dimensional version of Weisfeiler-Leman already. They kind of skipped over the 1-dimensional version. But I want to do the 1-dimensional version, and then we'll generalize to the higher dimensional versions, and that's where we'll see Bhattacharya-Mesner showing up. Okay, so I want to think of when I have a coloring at time t, so that assigns to each vertex some color, and my set of colors at time t is just whatever it is, it's some set, right? Whether you think of that as the nested multi-sets of blah, 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 or just you re-index your colors at time t to be some initial segment of the natural numbers, you have some set of colors at time t. So if I have a coloring like this, what I want to think of that is actually as a set of vectors where each vector is basically the indicator function of that color class. So for a given color C at a given time t, I'll have a vector. It'll be ones and zeros, and it's 1 on the vertices that have that color at that time, and it's 0 otherwise. So for a single coloring at a single time step, I get a collection of vectors, 1 for each color. Oh, right. And this is what I just said, that this vector is just the indicator, the 0, 1 indicator function of the color class. It's the set of vertices that have that color at that time. Okay. All right. And now we can define a sort of algebra here. So if I have a graph G with adjacency matrix A, I will call it 1WL algebra, WL for Weisfeiler-Leman. It's going to be a subspace of a vector space, and it's not super crucial that it's the complex numbers here. It's sort of useful that it's characteristic 0, but like even that's not crucial. But let me just leave it as the complex numbers for now. Of dimension equal to the number of vertices. So a 1WL algebra for this graph is a collection of vertices which contains the all ones vector. So that's like the indicator function of our initial coloring, right? Initially, every vertex has the same color. So there's only one color class and they're all in it. And if a vertex is in here, then when I multiply that vertex, if a vector is in here, when I multiply that vector by the adjacency matrix, that should also be in my algebra. Okay, and I want it to be closed under Hadamard product. Okay, and my claim is that these two properties exactly give us this process, allow us to do this process of coloring refinement, and essentially nothing else. Okay, so what I'm going to show you is how these two let us do color refinement. I'm not going to prove to you the nothing else part, that they can't do more than color refinement. Okay.
Sorry, Josh, one question.
Yeah. Mm-hmm.
What is the operation of the algebra?
Well, I guess in this case, it's just the Hadamard product.
But the Hadamard product of vectors.
Oh, and sorry, it's a subspace also. So you have linear combinations, and yes, Hadamard product of vectors. That's right.
Of what?
Vectors.
Of vectors.
Okay.
Right. So this is just like coordinate-wise product of the vectors. Okay. And you have this sort of exterior thing, which you can sort of think of your adjacency matrix as like an operator or like an additional scalar that you have, but it doesn't act like a scalar.
Operation, basically.
So you have a coloring kind of a vector version of that, and it's labeled. I'm just trying to.
Well, I'll do an example.
Okay.
Okay. Yeah. So actually, maybe let me skip to the example, and then come back to this thing about refinement. Okay. So, yeah. Okay. So let's do this graph. This was the one we were just looking at above, and here I've now numbered the vertices not by their degree. I've just given them all unique numbers so that I can write down their adjacency matrix. Okay. So this middle one, right? You see it has 5 neighbors. I've given that label 7, so that's 1, 2, 3, 4, 5, right? Those are its neighbors. It's an undirected graph, so this is a symmetric matrix. Okay. And now what I want to do is basically see the process of Weisfeiler-Leman, but in terms of these vectors and Hadamard product and so on. So we start out with our initial coloring, where all vertices are in the same color class. So I have the all ones vector, which I'll denote by this boldface 1. Okay. And now I say, well, my algebra, it has to be closed under linear combinations, which I'm sort of already done. I mean, I could scale this vector, but like that's not helping me do anything yet. Okay. It has to be closed under Hadamard product, but Hadamard product of this vector with itself isn't doing anything. And it has to be closed under multiplication by the adjacency matrix. So let's see what that does. So here, if I multiply this vector by the adjacency matrix, that's giving me a new vector, which is just adding up the rows here, right? Which is giving me the degrees, right? So this should be our degrees. It should be like chi1, almost. So let me not say that quite yet. All right, so first we get the degrees. So we see 1, 1, 1, 1, 2, 1, 5. Okay. Now I have this new vector in here. So let me call this vector V. This is not yet the indicator function of color classes, right? But I'm allowed to do scalar linear combinations and Hadamard products now. So here's what I can do. If I look at V minus the all ones vector, right? Because I have both of these vectors in here now. Okay, that cancels out all these ones and leaves me with 1, 4. Okay, and now I can do slightly clever things, which is I can say, well, really I should have 3 color classes here. So I want to get out 3 vectors from this corresponding to the 3 color classes, corresponding to the 3 different degrees that I see in this graph. So what can I do? Well, I can take this vector and let's see. Actually, let me just sort of pull out the magic formulas, but they're not magic. They come from somewhere. So right. So I can go that Hadamard B minus 2 times the all ones vector, and when I plug in 5, that should give me 4 times 3 is 12. So 1/12. This is the indicator vector of vertices of degree 5. Okay. Why? Because when I subtract off the all ones, right, that's giving me this. It's putting zeros in the places where there were ones before. And when I subtract off 2 times the all ones, it puts a 0 in the place where there was a 2 before. And when I take the Hadamard product, that puts zeros in all of those places. Yeah. Okay, but now when I plug in 5 here, this would give me 12. So I had to divide by 12 to get back this 1. Okay, so this is now using linear combinations and Hadamard product. I now got the indicator vector of vertices of degree 5. Okay, and you can do a similar thing. So that will kill off the 1s. This will now kill off the 5. And if I plug in 2 here, I get 1 minus 3. So I should have a minus 1/3 here. This will be the indicator vector of that vertex of degree 2. Okay. And then finally, I can kill off the 2s and the 5s. And when I put in 1, I get a minus 1 minus 4. So this should be 1/4. This will be the indicator vector of the vertices of degree 1. Okay. So from my adjacency matrix, I got this degree information. And then from the Hadamard product and the linear combinations, I could pull out these indicator vectors of the color classes I wanted. Okay, and now I'm not done. I'm not going to actually finish this, but you'll sort of see what happens. I now have more vectors. I need to multiply all of those by my adjacency matrix A also. And what is that doing? Well, multiplying this vector by A is telling you for each vertex, how many vertices of degree 1 is it adjacent to? Right, and multiplying this by A is how many vertices of degree 2 is it adjacent to? And this one is how many vertices of degree 5 is it adjacent to? Okay. All right, and so in this way, this sort of vector algebra completely captures this one-dimensional Weisfeiler-Leman process. Okay. All right. Yeah, so let me come back to this definition here. All right, so questions about the definition, and then we sort of already did this by example, but I'll walk through the general thing of how this gives you refinement. Okay, but now questions about back to this definition of 1WL algebra.
No, I don't think we have questions.
Okay, great.
I will ask something, but I want to see the whole thing when you get to the end of this
Yeah. Okay. Great. Good. Okay. So right. Okay. So the claim is that these two, multiplication by the adjacency matrix and closure under Hadamard product, give you this color refinement. And one thing I'll say is actually to have in mind is this adjacency matrix, I think, I'm not a physicist, but I think it sort of plays a role analogous to the metric tensor, like in the talks on the first day. It's sort of like a discrete version of the metric tensor, in the sense of the metric tensor is like local information about distances, and this, this is discrete information about distances, right? Like which vertices are distance one from one another. And in formulas, you'll see it sort of plays a similar role to how the metric tensor was showing up in the formulas on the first day. Okay. Let me see. How am I doing on time? Oh, okay. All right. Maybe I will skip this. We basically did this by example already. That multiplication by the adjacency matrix and closure under Hadamard product and scaling essentially lets you do this refinement process. Okay. So now what I want to do is I want to generalize this to the k-dimensional Weisfeiler-Leman algorithm, and this is where we'll see the Bhattacharya-Mesner product show up. Okay, so for k-dimensional Weisfeiler-Leman, instead of coloring vertices, we're going to color k-tuples of vertices now.
Josh, can I understand why is it called one-dimensional in the previous case?
Well, because of this. Because in the k-dimensional version, we're going to color k-tuples of vertices, and in the previous case, k was 1. That's the main. You'll also see that like it corresponded to vectors, and in the k-dimensional version, it will correspond to kth order hypermatrices, and vectors are like first, 1th order hypermatrices.
Yeah, that's why I'm a little bit confused about the use dimensional there. Wouldn't it technically be kth order in some sense?
Yeah, it should be order, but in the Weisfeiler-Leman literature, it's very standard that this is called k-dimensional Weisfeiler-Leman.
Yeah, I understand. Yeah. I'm not trying to change but technically the dimension was the
number in terms of the tensors. Yes, what this is called dimension should be order in terms of the tensors. Right. Okay. There's a complicated thing in that there's also a higher order version of Weisfeiler-Leman, which is even more complicated than this, and that also uses the word order.
Yeah.
And also has to do with tensors, but in a different way. And so I'm going to stick with dimension because it's like okay.
All good. Just wanted to understand this.
Yeah. So what I'll try and do is actually when I'm talking about Weisfeiler-Leman, I'll say dimension, and when I'm talking about tensors, I'll say order. And okay. All right. So for k-dimensional Weisfeiler-Leman, we're going to color now k-tuples of vertices instead of just vertices. Okay. And the initial coloring is now more complicated. It's by what's called the marked isomorphism type. So the initial coloring of two k-tuples is going to be the same if and only if any two of these vertices that are equal here, the same two have to be equal here. And for any two of these vertices here where there's an edge in the graph, there must also be an edge in the graph between those two vertices here. Okay, so I'll do some examples here. So when k is two-dimensional Weisfeiler-Leman, the initial coloring has 3 colors. So the colors of pairs, one color is when u equals v, right? So that's like this first condition, is if the two vertices are the same, that those pairs all start out with the same color, and that color is different than other pairs. Okay. Another color is the pairs which correspond to edges in your graph. And the third color is the pairs which correspond to non-edges in your graph. Okay, so that's our initial coloring of pairs. Okay, and then for k equals 3, the initial coloring has many more things. So one color class consists of things where all 3 vertices are the same. You get one color class where the first two are equal, the third one is different, and AB is an edge. You get another color where the first two are equal, the third one is different, and AB is not an edge. And you can sort of walk through all of these. Okay, and then finally, you also have what happens when all 3 vertices are distinct. It gets colored based on what the subgraph is. So here we have 1, 2, 3, 4, 5, 6, 7, 8 additional colors, depending on what that subgraph is on those 3 vertices. Okay. And one thing to note here is these are ordered k-tuples. And so these three subgraphs, although they're isomorphic, these actually correspond to tuples of three different colors, because you're keeping track of the order in which these vertices came in your tuple. Okay. All right. And then the refinement step is sort of similar to what happened before. So the new coloring at time t of a k-tuple is its old color, a pair consisting of its old color and a multiset. But now what that multiset is I'm going to look over all vertices in my graph, and I'm going to use that vertex u and replace each element of my k-tuple one at a time. So this is now a multiset of k-tuples of previous colors. Okay, and the idea here is that this k-tuple is sort of adjacent to this one in the sense of like they have Hamming distance 1. They just differ in one position, right? So before we were looking at neighbors, but now like what does it mean for two k-tuples to be a neighbor? Well, we'll just define it to mean they differ in one position. Okay. And for each vertex, we want to know if I choose to put that vertex in each of the possible k positions one at a time, what colors do I get? Okay. This one, unfortunately, it's very hard to do examples for even on small graphs because it gets very unwieldy very quickly. But at least in terms of like the formula and the concepts, are there questions here?
Is it?
Okay.
Is it?
Oh, yeah.
Just I mean, more than a question, it's just a clarification for my own understanding. Is it fair to say that these types are essentially labeling the vertex set, and then you're getting all these adjacency sensitive labels of larger subsets or tuples of your labeled vertices?
Yeah, that's essentially what's happening. Right.
Okay.
Yeah.
Okay. And so is it okay if I start to develop a picture in my mind where these are some kind of hypergraphs that are sort of being defined on the label set?
Yes, absolutely. Yep.
Okay.
Yeah, and actually, like I just like wrote a note, I don't know, a couple weeks ago when I was thinking about this that does exactly that and like connects it actually to some combinatorial topology stuff. Yeah, perfect.
Yeah. But carry on. Yeah.
Okay. Okay, so one thing to notice here, and we'll now get to this algebraic view, is this thing of like putting, in my k-tuple, in the first element of my k-tuple, I put u in the first position. In my second element of my k-tuple, I put u in the second position. In the kth element of my k-tuple, I put u in the kth position. This should sort of remind you of what's happening in the Bhattacharya-Mesner product. Okay, and this is where the connection is going to be. All right, so now we come to the algebraic view of k-dimensional Weisfeiler-Leman. So for k equals 2, actually, this goes back to Weisfeiler and Leman, who called these things cellular algebras, and to Higman, who called them coherent configurations. But for larger k, I kind of haven't seen this developed before. And I think it's because, I don't know, higher order tensors are scary and unwieldy, and okay, so now what I'll say is I have my graph and I want to define its k-dimensional KWL algebra to be a vector subspace of now I'm going to take the vector space I had before, which is vectors whose length is the same as the number of vertices I have, and tensor it with itself k times. Or if you like, this is a kth order box where all the side lengths are the number of vertices. Okay, and as vector spaces, this is isomorphic to a vector space whose dimension is the same as the number of k-tuples of vertices, right? Which is how we're going to connect it. Okay, so what should this algebra be? Well, it should contain all the I call these generalized diagonals. These are also related to these like units and biunits, and they may not be exactly the same, but by this I mean where you pick some partition of your indices and you put a 1 if the things in those parts are equal to one another and a 0 otherwise. So when in the 3-dimensional version, one of the generalized diagonals looks like this. It's the tensor T, where Tijk is 1 if and only if I equals j.
Yeah.
Right. So this is sort of like a generalized identity matrix or generalized diagonal.
Yeah. We I think we call them in our paper partial identities in general.
Partial identities, right?
Yeah.
Good.
So
right. Okay. And so this corresponds to that condition in the initial coloring of k-dimensional Weisfeiler-Leman, that you want to know which elements of your k-tuple are equal to one another. Right. This gives you all of those possible conditions. Okay. It should contain all the initial color classes for k-dimensional Weisfeiler-Leman. So that's this like marked isomorphism type thing. And I'll come back to that in a second. It should be closed under Hadamard product, and it should be closed under the Bhattacharya-Mesner product. And the claim is, just like before, that this one sort of by definition, this one gives you the initial color classes. But the claim is that these two let you do refinement.
So can you go to the one-dimensional one for a second?
Yeah.
Yeah. So.
Okay, so this all ones vector, this is like our generalized identity.
Yes.
Okay.
Yes.
Hadamard product is Hadamard product. This part is a little different. And actually, this is something I'm working out, is I think you can rephrase an equivalent definition to the one I just gave for k-dimensional in terms of something like this, where you're allowed to apply your adjacency matrix to any leg of your tensor you want.
Right.
And I just...
Because that was my question. What was A in this?
Yeah.
Right. So, okay. So in this definition, A is implicit here because the initial color classes now are not just these trivial things. They're these things about the marked isomorphism type of the subgraph. And that, of course, depends on A. So in some sense, A is showing up here.
Right.
Okay. But yeah, I think there should actually, I was thinking about this last night as I was going through these slides of like, I think there should be a way to rephrase this where you just start with these, you allow sort of multiplication by A in any direction and any of the legs. And I think you can get back this, but I'm not sure about that yet. So I don't want to. Okay. All right. Right. So Hadamard product basically lets you take the and of two color classes. Right. If I have the indicator functions of two subsets and I take their Hadamard product, that's the intersection. And Bhattacharya-Mesner is exactly doing this.
Yep.
Okay. Right. And so in some sense, like these, Bhattacharya-Mesner algebras, if you also ask them to be closed under Hadamard product and you have something coming from a graph like this, it gives you back exactly Weisfeiler-Leman. Okay.
Right.
So now, to close, I just want to point out a couple things. So when k is 2, I forget, I didn't see who it was who said this, but Carlos said this, right? When k is 2, Bhattacharya-Mesner is just matrix multiplication. Okay. The other thing to notice here, I now want to come back to this, is remember how I said in these initial color classes, we had things like this, right? Where this is one color class, this is another, this is another. These three color classes differ, if you think of these as third order hypermatrices, they differ just by transposing some of the legs, right? I've just put my things in a different order. Okay, so because the things I'm starting with are closed under permuting the legs in all possible ways, and these products, Hadamard and Bhattacharya-Mesner, preserve this property, this whole algebra is actually also going to be closed under permuting the k legs. And in the k equals 2 case, that just means matrix transpose, right? You only have two legs. Okay. So here what we have is we have an associative matrix algebra, right? Because the Bhattacharya-Mesner product is just matrix product. And it's closed under Hadamard product and transpose. And it contains the adjacency matrix of the graph. And some other things. The identity matrix, the all ones matrix. Okay. But the key thing that happened is closed under transpose for a matrix algebra implies that it is semi-simple. And in 1994, Ponomarenko used this to get an efficient algorithm for graph isomorphism when this semi-simple algebra has a bounded multiplicity of the irreducible representations that are appearing. So if you don't know what these words mean, that's fine. If you do, it's great. If you don't, the point is this is some algebraic thing that's coming out of this. It's not clear to me that this has a combinatorial interpretation at all. Okay. Okay. And so the question is now, since higher dimensional Weisfeiler-Leman corresponds to these higher order Bhattacharya-Mesner algebras, is there an analog of this, right? So here he's using the fact that this algebra is semi-simple very crucially. Okay, what does it mean for a Bhattacharya-Mesner algebra to be semi-simple, right? Here, again, he's using this thing about irreducible representations of this algebra very crucially. What is a representation of a Bhattacharya-Mesner algebra, right? And so some of the things that I'm thinking about now are these in general, but with the goal of, okay, we want to apply it to these algebras that are coming out of Weisfeiler-Leman. And so, yeah, this is very much work in progress. This is kind of where I'm at. And I'm very open to ideas and also collaborators and conversations and so on. All right, so that's what I wanted to tell you today. Thanks.
Right. Thanks very much, Stuart.
So nice. I have some questions.
Yes, go ahead.
No, but start.
No, cool. I don't have any minute.
Yeah, I wanted to ask more if you can go back to the algebra definitions or examples, because I was trying to work a bit on, I was getting familiar but very confused as well with Bernstein algebras recently. I don't know if you've heard about them.
No.
And I was wondering whether those algebras could be almost like a generalized version of those. And the reason why I'm saying that was because they have been used for proving the isomorphisms for graphs. I don't know how efficient was it, and was it more efficient than this WL method which you were referring to? And also the reason why I was saying, because they were identifying the Bernstein algebras ideas for helping with graphs, isomorphism, was essentially based on this idea that you would have, that for a graph, you would define equivalence classes, and two nodes would be part of one equivalence class if they would be adjacent to the same set of nodes. So that would have been kind of only like one very specific,
right?
Like there would be no definitions of the proper, right? Like the vector strings, they were not defining the vector strings essentially, but they were using only kind of almost like the first line of what you've done. They were not defining vectors, but they were. It was a bit different, right? But I was wondering if you heard about some simplified versions of those algebras.
No, I haven't. Yeah, and I would love, if you could send me some references or we could chat.
You some, yeah.
Yeah, that would be great.
Because
thank you.
What we're thinking that actually that could be interesting thing to do, because those things could be generalized. They could be rewritten for some ternary graphs, hypergraphs. I haven't managed to figure it out for other hypergraphs. It's maybe not because they're very well defined, but maybe there can be relations, because they use in the whole proof of two algebras would be, Bernstein algebras would be isomorphic if and only if the two graphs which they are constructed with are isomorphic. So it was kind of something that they were stating in their result. Right. That was the reason we were looking at them.
Right. Okay, great. Yeah, no, I would love to know more about that and talk with you about it for sure. Yeah. Oh, right. One thing maybe I should mention is it's known that like k-dimensional Weisfeiler-Leman for any fixed value of k does not solve graph isomorphism. Meaning for any value of k you choose. Oh, sorry.
Very good. Very good. Maybe it's because of that, because it's actually quite because it's a very kind of specifically also looking at something specific, but I don't know.
Right. Yeah. So the idea here is that like for a given k, it doesn't always solve graph isomorphism, but often it does. And when k is small, it's very easy to compute k-dimensional Weisfeiler-Leman. That's the key thing.
Yeah. So that was my question actually. Precisely because we were talking about these Burstyn algebras that Leo was mentioning, that they are constructed in this specific way where you get a graph isomorphism if and only if you have algebra isomorphism. To be honest, when you look at the construction of the algebra, you kind of realize it's kind of a bookkeeping construction. So it's not particularly insightful that you have that fact. It's not a particularly deep fact that you have isomorphism. But so basically, what do you know about the status of using this WL construction for the purpose of isomorphism in general? Is there what is the sort of
right. Yeah. So okay. So I didn't get into that in the background because I wanted to get to the algebra stuff. But lots of stuff is known. So like there are theorems even very recently about like an exact characterization of which graphs can be told apart by one-dimensional Weisfeiler-Leman. We know things like if you look in a class of graphs that exclude a fixed minor, so say like all planar graphs, or all graphs that are embeddable in a given surface, graphs in that class can be distinguished by Weisfeiler-Leman whose dimension is a constant, meaning independent of the size of the graphs. And I mean, there's a ton of stuff known, but one other thing I'll mention is it's also known that there's no fixed value of k that solves graph isomorphism. So and in fact, you need like k to be linear in the number of vertices in general. So there exists infinite families of pairs of graphs that are not isomorphic, but where the lowest dimension Weisfeiler-Leman that distinguishes them is linear in the number of vertices. So that's sort of like as strong as possible, right? Once you get up to n-dimensional Weisfeiler-Leman, like your initial coloring includes the isomorphism type of the graph by definition. Yeah, so a ton of stuff is known. And the thing that's interesting is even in spite of those known limitations, it still gets used as a subroutine in other algorithms for graph isomorphism all the time.
Right. That's interesting. So then maybe so I have two questions. So first, maybe the specific algebra question that you're pointing at about simplicity, for example. Yeah, can you remind us the definition of semi-simple in the binary case to maybe exercise what could be the ternary one?
Yeah, well, so the definition of semi-simple in the binary case, there are many equivalent definitions, and I'm not quite sure which, if any of those should generalize. So one of the equivalent definitions is all of its representations break up as direct sums of irreducible representations.
Yeah.
Okay, another one is there's this notion of a Jacobson radical, and an equivalent condition I should be a little careful, over fields of characteristic 0, I think I want to say, is that the Jacobson radical should be 0. Oh no, sorry, that one works in general. Sorry, that one doesn't need the restriction on the field. Right, so the Jacobson radical should be 0. Right, Wedderburn's theorem tells you that semi-simple means it's a direct sum of matrix algebras over division rings. So that is an equivalent characterization. I don't know. There are probably like a dozen equivalent characterizations, and it's not clear to me which ones. I sort of assume that it's like tensors, like the notion of rank for tensors, where like there are 12, equivalent notions of rank for matrices, and they all become inequivalent when you go to tensor, higher order tensors.
Right.
Yeah.
Yeah. So then I see why you are focusing on maybe the representation angle, because that seems to be a bit more transparent what to do there, right?
Well, maybe, right. And then the other thing is that like Ponomarenko has this algorithm where like it works when you have this condition on the representations is really the key thing. And one thing I'll say is this generalizes prior to Ponomarenko's paper, there was a paper by Grigoriev and Mount where they solved graph isomorphism in polynomial time for graphs with bounded eigenvalue multiplicity. So there's some constant where the eigenvalues don't appear with multiplicity more than that constant. And this condition about irreps of this semi-simple algebra actually generalizes that. Right. And so like, it's related to other things that people had looked at, but like stronger. And so that was sort of another motivation to try and go the representation rule is, can you generalize this result in particular, right? But to some version, some k-dimensional Weisfeiler-Leman instead of just two.
Right. Yeah. And the second question is, or comment is, have you thought what this implies, or how this helps somehow for, if you understand these colorings as hypergraph constructions? But incidentally, just if you want to go up to the part where you had the labels in the triangle, I think a couple of there. Yes. So interestingly, the way that we are encoding, and maybe this is as also kind of a note for people following the Wolfram Institute, we are developing a sort of a different way of encoding hypergraphs that computationally for our purposes. And it turns out that we actually kind of want to capture precisely this information in an edge for a generalized edge, that meaning that it can carry any sort of symmetry. We are looking at delimiting a bag of identified elements with unique labels like these types, ABC, and then you want to identify any graphic structure, like actual graphics, so two pairwise graphic structure on those vertices to essentially recover all manner of cyclic, symmetric tuple structures on those vertices, right? So just as a comment, this side comment that is interesting that this is the parallel. And then to me, it becomes very clear that these constructions, these colorings, the generalized colorings, they seem very much like what edges are looking like in how we define hypergraphs, for example. So have you thought about what this, because obviously the Bhattacharya-Mesner product is one particularly well-defined rule for rewriting, which essentially, when you think about it, is doing that. It's sort of associating several edges by saying there's a common intermediate vertex over here, right? So do you imagine generalizing any of these techniques with other motifs, like other products? Effectively, we know there are several hypermatrix products, right? That might be relevant. Have you thought about why Bhattacharya-Mesner specifically, but not others, or?
No. And one of the things that's interesting, I mean, okay, in this case, it's like, well, it's because it comes from this, and like people have, Weisfeiler-Leman is like a very well-studied thing, and there are tons of results about it, and Bhattacharya-Mesner is just what shows up because of this. Okay, but it actually gets back to the other thing I mentioned, that there are many like variants of Weisfeiler-Leman that all turn out to be roughly equivalent in power, even though they're not sort of equal on the nose, in the sense that, like, maybe the two-dimensional Weisfeiler-Leman of one variant is equivalent to like the four-dimensional Weisfeiler-Leman in another variant. Mm-hmm. Okay, but there's some constant factor between them. Like, that's what people mean when they say they're equivalent.
Yeah.
And yeah, it's easy for me to imagine that if instead of Bhattacharya-Mesner you used like one of these other hypermatrix products, that you might be doing some of these other variants of Weisfeiler-Leman, or you might be doing something totally new. Like, I haven't thought about it, but it's certainly an interesting question. Yeah. Yeah. And one of the things I'll say is, that when you get things that are equivalent in power but look different, that can actually be really useful. So like this, right? This result of Ponomarenko, it's somehow, it's okay. On the one hand, it's just about two-dimensional Weisfeiler-Leman, but somehow by rephrasing it in this algebraic way, he gets some power out of that, right? That, like, you're really talking about things where, like I said, I don't know a combinatorial interpretation for this condition, right? It's really an algebraic condition. And so you could also imagine by having different algebras, even though they're sort of equivalent, even if they are equivalent to some other version of Weisfeiler-Leman, having different algebras could give you these different viewpoints that could also still be useful and lead to new things. So yeah, no, definitely, I'd love to talk about that more.
Yeah. And one final question for me, and then if anyone else has more questions, then we can proceed. But do you see this helping in any way or shedding any light on the process of this term identity problem for the Bhattacharya-Mesner?
Oh,
do you get any insights from this angle for that?
It's an interesting question. I don't know. You could imagine that you could, for example, disprove identities by constructing graphs where this algebra, the Bhattacharya-Mesner product on this algebra did not satisfy the identity. Mm-hmm. Right. So you could kind of imagine, it's a little bit like the thing we had talked about previously, but I think it's actually different, of like, even if you want to have some Bhattacharya-Mesner identity that uses linear combinations also, you could imagine proving that something like that is not an identity by saying, well, if it has a certain form, then I can construct a graph where this algebra for that graph does not satisfy that identity. Mm-hmm. Right. So like, yeah, I mean, that's possible, but no, I haven't thought very much about it. Yeah.
Right. It's cool. Questions? Anyone?
Beautiful.
So one final comment I will make is, we've mentioned several papers, like the one you said with the Bernstein algebras, and several references here. If we could either email them to me or post them directly on the Discord somehow, I'll gather them all up and I'll put them on the specific channels of the Discord on the Wolfram Institute community. So because I think there's some really interesting papers here. I think the paper you found contrasts interestingly with this WL construction.
Yeah, I really wonder the connection, because it was, I can post more the notes that I tried to make to generalize it, but it was not finished.
It's
one other comment.
Yeah.
That I'll make here is, so this gets back to your question before of, okay, I think you can rephrase this as basically you omit this condition, you just start with the generalized diagonals, but you allow multiplication by A on any of the legs. Mm-hmm. That also, thinking about that and trying to work that out, which I haven't yet, but I think something like that should work, is also where, I was watching these talks from Monday and I was like, this A is almost like playing the role of this metric tensor, right? Where it's like you can hit sort of any leg you want with it. And so this is another place where that analogy is showing up.
In a specific way, I mean.
No, just to rephrase this thing.
Yeah.
So it's just using, because A, so it's interesting because A is a bit of pairwise information. It's sort of what reminds you that you began with a graph, a proper pairwise graph.
Right.
And you could even imagine generalizing this for hypergraphs. So instead of starting with an A, you start with some other hypermatrix proper, and then you can,
and actually you can do Weisfeiler-Leman, like Weisfeiler-Leman like this. It is actually very general. Like you can do it for hypergraphs. You can also define things like this sort of for any finite structure in a first order language with relations and functions or something like that. Like it gets very general, but the initial coloring idea and that it's sort of marked isomorphism type and the refinement step sort of are always the same.
Great.
Nice.
Very nice, Josh. That was very interesting. And nicely presented. Very clear.
Great. Thanks.
And
Yeah.
beautiful.
Thanks again for having me. Yeah.
No, our pleasure. And hope the holiday is going well.
Yes. Thank you.
So, anyway, unless there are any other comments, I think it's a good point to, it's been a long day here. So we can call it. Yeah, it's in the evening already here. So as I said, if you can send all the relevant references, just maybe send them over email and I'll compile them and put it in the right channels and everything. But otherwise, thank you so much. Thanks, James, also for the logistics in the background. We are live on YouTube, and thanks for everyone joining us, lurking in the interwebs. I know that there are a few people watching over there. So, thanks, everyone. Thank you, everyone here.
Thank you, Carlos.
Great.
Bye, everyone.
And Richard.
Goodbye.
Yeah, thanks, team.
See you.